Chocolate chip cookies, biscuits, and oat bars are mass-produced to deliver the same crunch and sweetness in every bite. Inside industrial bakeries, mixers whip dough to exact consistency, and oat blends are pressed and baked into dense bars. In this video, we follow the full line from ingredient silos to heat-zoned ovens, revealing how portioning and packaging controls keep each product shelf-ready. Chocolate chip cookies are manufactured by building a controlled dough system, portioning it into uniform pieces, baking to a defined moisture gradient, then cooling and packaging to preserve crispness or softness depending on the target style. Production starts with ingredient conditioning because dough behavior depends on temperature and particle size. Flour is sieved to remove lumps and to aerate it for consistent hydration. Sugar is managed as two streams when both granulated sugar and brown sugar are used. Granulated sugar is screened for consistent crystal size. Brown sugar is broken down to remove hard clods because clods create dark pockets and uneven spread. Fats are conditioned to a plastic state so they cream smoothly and do not separate. Eggs or liquid egg products are tempered to a consistent temperature so they emulsify predictably. Chocolate chips are stored cool so they keep shape during mixing and do not smear into the dough. The mixing sequence begins with creaming because it sets the cookie structure. Fat and sugar enter a mixer with a paddle tool that shears and folds. Creaming disperses sugar crystals through fat and traps small air cells. The amount of trapped air influences cookie lift and interior texture. Mixing time is controlled so air incorporation stays consistent. Over-creaming yields excessive spread variation and fragile cookies. Under-creaming yields dense cookies with limited rise. If the formula uses brown sugar, its molasses content changes water binding and dough viscosity. Brown sugar is added early in creaming so it breaks down and disperses. The ratio of brown to white sugar controls spread and chew because molasses holds moisture and affects browning. Salt and leavening can be added during creaming so they distribute evenly. Leavening selection matters because baking soda promotes spread and browning, while baking powder adds lift. Eggs are added next to build an emulsion and hydrate proteins. Eggs are introduced gradually so the fat phase does not break. The mixer runs at a speed that maintains a stable emulsion. If eggs are dumped in too fast, the mixture curdles and the dough becomes inconsistent. Vanilla and other flavors are added with the egg stream because they disperse well in the liquid phase. Dry ingredients enter after the fat and egg system is stable. Flour is added in controlled increments to avoid dust and to prevent dry pockets. Mixing energy is reduced during flour addition because gluten development must be limited. Too much gluten makes cookies tough and reduces spread. The endpoint is a cohesive dough where flour is hydrated but the structure remains short due to fat coating. If the recipe includes starches or milk powders, they enter with the flour. Starch can soften texture by reducing gluten strength. Milk powders can increase browning and add dairy notes. Each addition changes water demand. Water demand is managed by egg level and by added water if used. Dough temperature is tracked because warm dough spreads more in the oven. Chocolate chips are added at the end of mixing to preserve chip integrity. Chips are folded in at low speed so they distribute without breaking. Distribution uniformity matters because each cookie needs a consistent chip count. Mixing after chip addition is kept short to avoid smearing chocolate into streaks. If chips are warm, they can melt and create muddy color. Chip temperature control prevents that. Once mixed, the dough often goes through a short rest. Rest allows flour hydration to complete and lets the dough firm as fats stabilize. Rest also reduces stickiness and improves portioning accuracy. Dough can be held in a cooled hopper to maintain a consistent temperature band. Consistent temperature is critical because it affects extrusion rate and cookie spread. Portioning converts bulk dough into individual pieces with defined mass. High volume lines use wire cut or rotary molded or depositor systems. Wire cut systems extrude a dough log through a die, and a moving wire slices portions. Die shape sets cookie diameter. Wire timing sets piece weight. Rotary mold systems press dough into engraved rollers that form shaped pieces. Depositors drop measured dollops for soft-style cookies. Each method relies on stable dough viscosity. During portioning, the dough is placed onto baking trays or oven bands. Spacing is controlled because cookies spread during baking. If pieces are too close, they merge. Spacing is managed by indexing belts and by tray loading patterns. Weight checks verify portioning accuracy because mass affects bake time and moisture. Baking is a staged heat process that sets shape and creates the desired texture. Cookies enter a tunnel oven with multiple zones. Early zones apply heat that melts fats and starts spread. As spread occurs, the cookie surface begins to set. Leavening gases expand and create internal porosity. Steam is generated from water in the dough and it contributes to lift. As baking continues, proteins coagulate and starch gelatinizes, then dries. These transitions transform dough into a solid matrix. Sugar dissolves in the early wet phase and then begins to recrystallize as moisture leaves. This sugar behavior affects crispness. The Maillard reaction and caramelization drive browning and flavor development. Oven temperature and airflow set the rate of these reactions. Texture is controlled by managing the moisture gradient. A crisp cookie is baked longer, so moisture drops low through most of the thickness. A chewy cookie is baked to leave more moisture in the center while the edges set. This requires careful control because the outer region can overbrown before the center hits target. Oven zones allow the line to drive strong, top heat early for structure, then moderate heat later for uniform drying. Airflow affects surface drying and color. High airflow removes moisture quickly and increases crispness. Lower airflow allows more moisture retention. Some ovens use impingement jets that drive heat into the surface rapidly. Others use convection with gentler airflow. The chosen profile is tuned to the dough formulation and piece size. Cookie spread is controlled by dough fat type and sugar ratio and dough temperature and early oven heat. If spread is excessive, cookies become thin and fragile. If spread is insufficient, cookies stay thick and can remain underbaked in the center. Lines adjust by changing dough temperature and by adjusting the first oven zone temperature. They can also adjust piece weight slightly to influence final diameter. When cookies exit the oven, they are fragile because the structure is still hot and fats are liquid. They move on to cooling conveyors that support them and prevent bending. Cooling must be controlled because rapid cooling can create cracking in crisp products. Gradual cooling allows structure to set as fats crystallize. Cooling also allows moisture to redistribute slightly within the cookie. This redistribution affects final texture. A cookie that feels soft when hot can become crisp after cooling as moisture equilibrates. For soft cookie styles, the process may include a rapid cooling step that limits moisture loss. For crisp styles, the process may include extended cooling with dehumidified air to drive moisture lower. Air humidity control matters because cookies can absorb moisture from humid air and lose crispness. Cooling tunnels therefore often use conditioned air. After cooling, the cookies may be inspected and sorted. Vision systems can reject merged cookies and broken cookies, and off-color pieces. Metal detection can be placed after cooling to protect final product flow. Sorting also aligns cookies for packaging and removes crumbs that would contaminate seals. Packaging is designed around moisture control because cookie texture is moisture sensitive. Crisp cookies require high barrier film that prevents water vapor ingress. Soft cookies require packaging that limits moisture loss so they do not dry out. Many lines use flow wrappers that seal each cookie or stacks of cookies. Film is formed around the product and sealed longitudinally and at the ends. Seal integrity is critical because small leaks change texture over time. If cookies are packed in trays, the trays protect against breakage. Cookies are loaded into plastic trays by robotic pick and place or by lane collators. Trays are then wrapped in film. Trays also control headspace and reduce movement that generates crumbs. For bagged formats, cookies are collated into stacks and then dropped into bags. Stack height and alignment are controlled so the bag seals cleanly. Biscuits are manufactured by converting flour, fat, sugar, and leavening into a stable dough, shaping that dough into uniform pieces, baking to a defined moisture endpoint, then cooling and packaging to preserve texture. Production starts with flour handling because flour properties control dough strength and spread. Flour is delivered in bulk and routed through sieves that remove lumps and foreign particles. Aeration during sieving improves consistent hydration. Flour temperature and moisture are monitored because they affect water demand. If flour is warm, the dough softens and smears in sheeting. If flour is cold, the dough can crack and resist forming. The line, therefore, conditions flour to a narrow temperature range before mixing. Sugar is prepared based on biscuit style. Granulated sugar is screened to control crystal size and reduce dust. Powdered sugar is delumped because hard clods create white streaks. Brown sugar is broken down and evenly distributed because molasses pockets create dark spots. Salt is weighed and kept dry so it flows consistently into feeders. Leavening agents are staged separately because their particle size and reactivity affect lift. Fats are tempered to a plastic consistency so they disperse evenly and limit gluten development. Water and liquids are prepared with controlled temperature. Water temperature is used as a mixing control lever. Warmer water speeds hydration and shortens mixing time. Cooler water firms dough and improves machining. Syrups and dairy liquids are held in jacketed tanks if used. Liquid egg or milk can be included for richer biscuits, and it is tempered to avoid curdling in the fat phase. Mixing begins with a sequence selected to manage gluten. For short, crisp biscuits, the process aims to limit gluten formation. Fat is combined with flour early to coat flour particles. This coating reduces water access and reduces gluten development. Mixing equipment uses paddles or sigma blades that fold and smear fat into flour without overworking. Sugar and salt can be added at this stage, so they distribute through the fat-coated flour. Water is then added gradually while mixing continues at controlled speed. The aim is to hydrate enough to form a cohesive dough while keeping it short. Overmixing develops gluten and makes biscuits tough. Undermixing leaves dry pockets that tear during sheeting. The mixing endpoint is judged by dough uniformity and by torque and by visual cohesion. For semi-sweet biscuits or cookies, the line may use a creaming step. Fat and sugar are creamed to incorporate air and create a lighter structure. Liquids are then added to form an emulsion. Flour is added last and mixed briefly. This method yields more spread and a different crumb structure. Both methods rely on controlling dough temperature and mixing energy. After mixing, the dough often enters a rest stage. Rest allows moisture to distribute through flour particles. Rest also lets the dough relax and reduces elastic snapback. Reduced snapback is important for precise cutting and consistent size. Rest temperature is controlled because warm rest softens fat and changes dough stiffness. The dough then moves to forming, which can be sheeting, extrusion, or molding. Sheeting is common for many biscuits. Dough passes through reduction rollers that gradually decrease thickness. Multiple passes avoid tearing and keep texture uniform. Gauge rollers set the final thickness. Thickness control is crucial because it sets bake time and final moisture. Dusting flour can be applied during sheeting to prevent sticking. Dusting must be minimal because excess dust burns and creates bitter specks. The line uses controlled dusting and brushes to remove excess. Dough temperature is controlled during sheeting because warm dough sticks and cold dough cracks. After sheeting, the dough is cut into shapes. Rotary cutters punch biscuits from the sheet. Cutter dies define shape and size. Scrap dough is lifted away and recycled. Scrap handling is controlled because repeated recycling can toughen dough by building gluten. Many lines limit scrap ratio by controlling sheet width and cutter layout. Docking is often used for flat biscuits. Docking pins punch small holes in each piece. Holes allow steam to escape during baking. This prevents blistering and ensures flatness. Docking pattern influences surface appearance and break strength. The docking station is synchronized with cutter speed so holes stay centered. For molded biscuits, a rotary molder can be used. Dough is pressed into engraved cavities on a roller and then released onto a conveyor. This method creates surface patterns and can handle softer dough. Release depends on dough fat level and temperature. If dough is too warm, it smears in cavities. If too cold, it cracks and does not fill details. Extrusion can be used for certain biscuit forms. Dough is forced through a die to create a continuous rope. The rope is cut into segments or shaped further. Extrusion requires dough with consistent viscosity. Viscosity is controlled by water level and fat plasticity. Formed pieces are transferred onto baking bands or trays. Transfer must avoid deformation. Conveyors use gentle acceleration and minimal drop heights. Spacing is controlled because pieces can spread or expand slightly during baking. If pieces are too close, they can merge. Baking is the main transformation stage. Biscuits enter a tunnel oven with multiple heat zones. Early zones apply heat that sets surface structure. Fat melts and the dough begins to relax. Water begins to evaporate and steam forms within the piece. Leavening reacts and produces gas that creates internal porosity. As baking continues, starch gelatinizes, then dries into a rigid matrix. Proteins coagulate and contribute to structure. Sugar dissolves in the early wet phase and then participates in browning reactions as moisture falls. Maillard reactions and caramelization develop color and flavor. Oven temperature and airflow control the rate of these reactions. Moisture endpoint is a primary target because it defines crispness and shelf stability. For crisp biscuits, the line drives moisture low so the biscuit fractures cleanly. For softer biscuits, the line stops earlier to retain more moisture. Moisture control is managed by oven profile and by piece thickness. A thicker biscuit needs longer bake or higher heat. A thinner biscuit can overbrown quickly if heat is too high. Airflow influences drying and surface texture. Strong convection removes moisture fast and yields a drier surface. Gentler airflow allows more, even internal drying. Many ovens use independent top and bottom heat control. Bottom heat drives structure set from the band side. Top heat drives surface color. Balancing top and bottom heat prevents warping and ensures even bake. Spread and shrink are managed through dough formulation and early oven conditions. If early heat is low, the dough can spread too much before setting. If early heat is high, the surface sets quickly and limits spread. The line adjusts the first oven zone to tune diameter and thickness. After baking the biscuits, exit hot and fragile. They move to cooling conveyors where they firm as fats resolidify. Cooling also allows moisture to redistribute slightly. For crisp biscuits, cooling air is often dehumidified because biscuits can absorb moisture from humid air and lose snap. Cooling is staged, so thermal stress does not crack the biscuits. During cooling, the biscuits are inspected and sorted. Vision systems can detect overbaked color and broken pieces and misshapes. Metal detection can be placed after cooling. Crumb removal systems collect loose fragments that would contaminate packaging seals. If the product includes surface toppings such as sugar crystals or salt or glaze, the application is timed to surface condition. Sugar sanding is often applied before baking so crystals embed and partially melt. Glaze can be applied after baking and then dried lightly. These steps require separate dosing systems and add additional moisture management considerations. Packaging is designed to protect biscuits from moisture and breakage. Biscuits are collated into stacks and oriented. Stacking systems use lanes and pushers to form uniform packs. The packs are then flow wrapped or placed into trays. Flow wrapping uses barrier film that blocks water vapor. Tray packs provide mechanical support and reduce breakage during transport. Seals must be clean because crumbs can interfere with seal integrity. Packaging machines use crumb extraction near the seal jaws. Film tension and seal temperature and dwell time are controlled, so seals are tight. Coating is applied for traceability. Check weighers confirm count or weight. Oat bars are manufactured by converting oats and binders into a cohesive slab, setting that slab by baking or cooling, then cutting it, and packaging so texture and moisture stay within a tight window. Production starts with oat preparation because particle size distribution controls chew and structural strength. Rolled oats are screened to remove fines and oversized flakes. Fines create dust and can make bars dense and crumbly. Oversized flakes create weak points and poor cut edges. If the product uses oat flour or milled oats, that stream is prepared separately and sieved to prevent clumps. Nuts, seeds, or crisp inclusions are sized and cleaned so they do not introduce hard fragments that damage cutters. Sweetener and binder streams are prepared in parallel. Glucose syrup or similar syrups are held in jacketed tanks to maintain a stable viscosity for pumping. Sugar can be added as granulated crystals or dissolved into a syrup depending on the texture target. Fat sources such as vegetable oil or butter are melted and held at controlled temperature. If nut butters are used, they are warmed to a flowable state and mixed to eliminate oil separation. Emulsifiers can be staged to stabilize the binder and improve coating of dry particles. Dry minor ingredients are pre-blended to ensure uniform distribution. Salt is weighed and dispersed to prevent salty pockets. Leavening is used only in certain baked styles, and it is weighed precisely. Protein powders or milk powders are sieved because they form lumps when exposed to binder. Spices and flavors are blended into the dry premix or injected into the binder depending on volatility. The process creates a binder first because the binder must coat every dry particle quickly. A heated mixing kettle combines syrups and sugars and fats. Agitation keeps the mixture homogeneous and prevents hot spots. Temperature is raised to dissolve sugar if needed and to reach a target solids level. Solids level controls final stickiness and water activity. If solids are too low, the bars remain sticky and can weep. If solids are too high, the binder becomes glassy and the bar becomes hard. Cooking is used in many oat bar lines to adjust binder concentration. The binder is heated to drive off water and to raise viscosity. Time and temperature are controlled because overheating darkens sugars and changes flavor. When the binder reaches target viscosity, it is cooled slightly to a mixing temperature that will not damage heat-sensitive inclusions. Cooling also prevents excessive softening of oats during mixing. Flavor addition often occurs after this cooling step. Vanilla and spice extracts are injected, so aromatics are preserved. If fruit concentrates are used, they are blended in at controlled temperature. because they can burn or separate when overheated. Acidulants can be added to balance sweetness and also to manage microbial stability. The binder is mixed until it is uniform, and then it is pumped to the forming line. Dry blending begins with oats as the primary structural phase. Oats are loaded into a ribbon blender or a paddle mixer. The mixer runs at low speed to avoid breaking flakes. If nuts or seeds are included, they are added and distributed. Dry powders, such as protein, are added as a pre-mix to reduce streaks. The dry blend is mixed only until distribution is uniform because overmixing generates fines. Binder is then introduced into the dry blend. The binder is metered by mass flow, so the ratio remains stable. It is delivered through spray bars or a manifold that distributes it across the mixer width. The mixer switches to a folding action that turns the dry blend through the binder stream. The goal is rapid coating without crushing inclusions. Coating uniformity is critical because uncoated oats fall apart and overcoated zones become sticky clumps. Mixing endpoint is judged by appearance and by torque. The mass should look uniformly glossy with no dry pockets. It should flow as a cohesive mixture but still show discrete oat flakes. If the mass is too wet, it will smear during forming and create dense bars. If it is too dry, it will not bind and will shed crumbs during cutting. Temperature during mixing is monitored because warm mass flows better but can collapse structure later. Once mixed, the mass is transferred to a forming system that creates a continuous slab. Transfer chutes are designed to reduce segregation because heavier inclusions can settle. Many lines use a short transfer distance and a low drop height. The mass is fed onto a moving belt through a spreader that distributes it to full width. The spreader uses leveling bars and rotating paddles to create an even bed height. Compaction follows spreading and it defines bar density. A set of compression rollers presses the mass to a target thickness. Roller pressure and gap determine final thickness and porosity. Higher compression yields a dense bar with fewer voids and a cleaner cut. Lower compression yields a lighter bar with more chew and visible structure. Compression must be uniform across the belt to avoid thickness variation. If the product includes a base layer such as chocolate or yogurt coating, the sequence can include a bottoming step. A thin film is applied to the belt and partially set before the oat mass is deposited. This creates a bonded base that can act as a moisture barrier. The base layer thickness must be controlled because it affects cutting and packaging. Setting the slab depends on product style. For baked oat bars, the slab enters a tunnel oven. Baking drives off moisture and sets structure by solidifying sugars and fats. Oven zones are tuned to avoid overbrowning while reaching a target moisture endpoint. Airflow and temperature control surface drying and internal set. The slab must be firm enough to cut cleanly, but not so dry that it becomes brittle. For no bake oat bar setting is achieved by cooling rather than baking. The slab enters a cooling tunnel where fats crystallize and binders firm. Cooling profile is staged to prevent cracking. Rapid surface cooling can create a hard skin while the core remains soft. A staged profile cools evenly and yields a uniform firmness for cutting. Moisture control is critical in both styles. Oat bars sit in a moisture window where they are not sticky but still chewy. Too much moisture leads to stickiness and microbial risk. Too little moisture leads to hardness and crumbling. The process controls this window through binder solids and oven time or cooling time. Water activity is measured on samples and used to adjust settings. After baking or cooling, the slab may be conditioned before cutting. Conditioning allows temperature and moisture to equalize across the slab thickness. This reduces internal stress and prevents edge cracking. Conditioning also stabilizes the surface so blades do not drag. For baked slabs, conditioning can include a short cooling stage to bring the slab to a consistent cut temperature. Cutting converts the continuous slab into bars with defined weight. A first cutter trims the edges because edges can be uneven from spreading. Trim is collected for rework depending on recipe constraints. The main slab then passes through a guillotine cutter that creates long strips. A cross cutter then divides strips into bar lengths. Blade speed and sharpness are tuned to avoid tearing oats. Warm slabs can smear and stick to blades. Cold slabs can fracture and generate crumbs. If the product includes a top drizzle or enrobing, the coating step can occur after cutting. Chocolate is tempered and then applied as a curtain or as a drizzle. Drizzle heads deposit controlled lines. Enrobing coats the bottom or full bar. Coatings are then set in a cooling tunnel. Coating application must avoid adding excessive heat that softens the bar matrix. Dunkin Donuts production starts with formulation of base dough using a high-capacity spiral mixer. Ingredients are loaded automatically through overhead dispensers connected to silos and tanks. The dry phase includes high-gluten wheat flour, sugar, salt, non-fat dry milk, and dough conditioners. Liquid components include water, whole eggs, vegetable shortening, and yeast. Ingredients enter the mixing chamber in a fixed order to ensure consistency. Flour is dispensed first into the bowl, followed by sugar and salt through calibrated rotary valves. Shortening is pre-melted in a jacketed vessel and dosed into the bowl using a metered pump. Liquid eggs are held in chilled tanks and dispensed through a pneumatic valve. Yeast is hydrated in a separate tank before being introduced into the mix stream. Mixing begins at a low speed to hydrate the flour and form gluten strands. The mixer transitions to a higher speed to fully develop elasticity. Total mixing time ranges between 8 and 12 minutes depending on batch size and target temperature. Bowl temperature is monitored through probes to prevent overheating. Once dough reaches optimal extensibility and temperature, it is discharged into a dough handling conveyor. This conveyor feeds a volumetric divider equipped with servo-driven pistons that portion dough into uniform units. Each portion is shaped into a ball using a rotary rounder. Rounded dough balls are transported by a belt conveyor into a multi-level proofer cabinet. Inside the cabinet, humidity and temperature are controlled to activate yeast fermentation. The dough rests for 30 to 60 minutes based on size and environmental conditions. After proofing, dough pieces exit the cabinet and enter a forming machine configured for ring shapes. A sheeter flattens each piece to a fixed thickness. A dual-blade rotary cutter stamps the dough into rings and removes the center to create the hole. Waste dough is automatically conveyed back to the hopper for reprocessing. Cut dough shapes are placed onto paper-lined proofing trays by a pick-and-place arm. Trays are loaded onto racks that feed into a secondary proofer tunnel. This tunnel maintains consistent humidity and temperature for final rise. Final proofing continues until dough height reaches preset targets. Proofed rings are then transferred onto a mesh belt conveyor leading into the frying system. The fryer is filled with vegetable oil, maintained at 190 degrees Celsius using immersion heating elements. The belt submerges each donut halfway and flips it midway to ensure even browning. Frying time is approximately 90 seconds per side. Excess oil is removed at the fryer exit using an inclined drip section. A vibrating shaker assists in shedding residual surface oil. Donuts proceed to a cooling conveyor that circulates ambient air over the surface to reduce internal temperature before finishing. Cooled donuts are sorted into finishing lines based on type. Plain rings move to the glazing station, which includes a curtain coater that pours warm sugar glaze over moving donuts. Excess glaze is recovered by a recirculation pump. Coated donuts pass under an air knife to remove drips and ensure uniform coating. For powdered sugar varieties, donuts are diverted into a tumbling drum. Fine sugar is dispensed into the drum continuously as donuts rotate inside. The tumbling motion creates full surface coverage. Sugar fines are filtered and reused through a vibratory sifter. Chocolate-coated donuts are transferred to an enrobing line. Melted chocolate compound is maintained at 38 degrees Celsius in a reservoir and pumped to a waterfall applicator. Donuts pass under the waterfall and receive a full coating. An inline cooling tunnel solidifies the chocolate layer. Filled donuts follow a different path. These start as solid discs cut from sheeted dough and proof separately. After frying and cooling, each unit is aligned on a conveyor with a multi-nozzle injection machine. The filling system uses positive displacement pumps to inject jelly, custard, or cream into each donut at a fixed volume. Nozzles penetrate the side and retract automatically after filling. Decorated donuts are moved to a robotic icing station. Each robot arm uses a temperature-controlled piping nozzle to apply icing patterns or toppings. Sprinkles are deposited via gravity-fed hoppers positioned above a vibrating grid. Icing is cooled rapidly with a chilled air tunnel to prevent smearing. Donuts requiring packaging are grouped using a photo eye sensor and placed into trays by a robotic loader. Trays are conveyed to the overwrapping station where a film is wrapped and sealed using a heated jaw. Packaged trays proceed to a labeling machine that applies product and date information. Donuts intended for retail stores are stacked into crates by a pusher arm. Crates are conveyed to a loading dock and stored in temperature-controlled bays before transport. Crate movement is sequenced based on product age to maintain first-in, first-out flow. Throughput is maintained by synchronizing mixing, proofing, frying, glazing, filling, and packing stages. Any discrepancy between steps is corrected by buffer zones built into the conveyor system. Sensors at each handoff point check for weight, position, and spacing. Dough properties are controlled through water temperature, flour hydration, and mixer speed. Yeast activity is adjusted using proofing time and sugar content. Fry color and texture are determined by oil temperature, dwell time, and surface evaporation rate. Glaze thickness is adjusted by flow rate and curtain gap. Chocolate viscosity is controlled with continuous mixing and temperature monitoring. Filling density depends on nozzle diameter and injection pressure. Sprinkle adhesion is determined by icing tack time and coating temperature. Rework dough is monitored to prevent excessive cycles which could affect gluten structure. Oil is filtered continuously through a mesh screen and replenished to maintain performance. Icing and glaze are discarded after exceeding hold time limits. Mechanical components are cleaned using a clean-in-place system for mixers and pumps. Fryer oil is drained and replaced after a fixed number of cycles. Filling stations are purged between flavor changes using heated rinse cycles. Donut size is kept uniform through automated cutting, proofing, and handling. Each unit is weighed inline using load cells before frying. Out-of-spec pieces are rejected by air jets and sent to waste bins. Color is monitored by optical sensors after frying and coating. Each production run is tagged with a digital identifier that tracks every batch of dough from mix to packaging. Operators interface with the line through touchscreen HM that adjust process parameters and initiate recipe changes. The ring shape is maintained by cutter pressure, proofing time, and dough elasticity. Hollow centers expand predictably when gluten structure and gas production are balanced. Sidewalls form evenly when frying is performed at the correct temperature gradient. Filled donuts expand less during frying due to the absence of a central void. Filling volume is calibrated to prevent leakage and to ensure weight compliance. Injection heads are sanitized between runs using a self-cleaning piston flush system. Production of limited-time donuts uses custom molds or dies fitted to the standard sheeting line. These are swapped in and out using quick-release clamps mounted on the cutting head. All process conditions remain unchanged except for shape and possibly finish. The Dunkin Donuts production process is defined by sequential control over dough preparation, shaping, frying, finishing, and packaging. No stage is manually operated after initial ingredient loading. All transfers are automated and time synchronized. Mechanical reliability is ensured through routine calibration of volumetric dividers, fryer controls, coating pumps, and injection systems. Sensors detect clogging, misalignment, or loss of temperature and alert the PLC for correction. Air quality around finishing zones is maintained using filtered ventilation that prevents icing contamination. Powder applicators are enclosed and use vacuum returns to contain sugar dust. Chocolate lines are enclosed and climate controlled to prevent blooming. Every donut passes through at least 8 separate mechanical systems before final packaging. Each system modifies dough, temperature, texture, filling, or coating in a defined and repeatable way. The outcome is a donut with precise dimensions, weight, color, and taste profile. Wendy's burgers begin with raw ground beef held in refrigerated stainless steel bins, fitted with auger-driven dispensers. The beef is pre-ground to a fixed particle size and loaded into a hopper positioned above the patty forming system. The patty forming machine uses a hydraulic ram to compress a measured quantity of beef into a square mold. The square mold consists of a cavity with sharp edges and adjustable depth to control thickness. The beef enters the mold vertically and is pressed to a target shape using downward force. A release plate ejects the formed patty onto a conveyor belt lined with a non-stick food-grade belt material. The patties travel on the belt to a pre-cooked staging zone where they are spaced using an optical sensor and gating arm. Each patty is indexed into a clamshell-style contact grill, which applies uniform pressure from above and below. The upper platen is heated with embedded electrical elements and lowered using pneumatic pistons. The bottom platen remains fixed and maintains a set temperature through thermal sensors. Cook time is controlled by belt speed and platen temperature. Average dwell time for each patty is between 100 and 120 seconds, depending on thickness and grill load. Internal patty temperature is monitored using inline thermal probes, which retract automatically after contact. Surface browning is caused by Maillard reactions accelerated by the grill temperature. Rendered fat drains through grooves in the lower platen and is collected in a drip pan. Excess steam is evacuated through a hood system positioned directly above the grill zone. Once cooked, the patty exits the grill and moves onto a staging tray held at a constant holding temperature using a heat lamp array. While patties are cooking, buns are prepared on a separate toasting line. Buns arrive from storage in trays and are unloaded onto a conveyor. The bun separation system uses rotating paddles to split top and bottom halves and align them face down on the line. Each bun half passes under a radiant toaster element which operates at a fixed distance above the surface. Toasting time is determined by conveyor speed and element intensity. Bottom buns are toasted slightly longer than top buns to handle moisture from toppings. After toasting, buns proceed to the assembly belt where they meet other components. Burger toppings are prepared on parallel preparation lines. Leaf lettuce is pre-cut and washed, then stored in chilled bins and dispensed manually into bins along the line. Tomatoes are sliced using a rotary blade slicer that maintains uniform thickness. Slices are collected into trays and moved to the topping line by belt conveyor. Onions are peeled and cut using an automated ring slicer and loaded into shallow pans. Pickles are pre-sliced and held in brine-filled containers until use. Cheese slices are separated by a vacuum picker and fanned out onto a chilled tray. Condiments, including mayonnaise, ketchup, and mustard, are dispensed using trigger-activated pumps that release a fixed volume per stroke. Dispensers are calibrated to deposit evenly without spread beyond the bun area. Burger assembly begins with bottom buns moving along a belt aligned with the topping line. A pump dispenses mayonnaise directly onto the bun in a circular pattern. A square cooked patty is placed onto the bun using a precision-guided placing arm, or manually depending on station configuration. Cheese slices are placed directly on top of the hot patty, which softens the cheese slightly but does not fully melt it. Sliced tomato is added next by tongs or fingers placed at center alignment. A leaf of lettuce is layered over the tomato and adjusted to not overhang the bun. Onion rings are laid flat across the lettuce with no stacking. 2 or 3 pickle slices are placed side by side depending on diameter. Ketchup and mustard are dispensed in zigzag or dot patterns based on the specific burger recipe. The top bun is retrieved from its place on the parallel conveyor and inverted onto the built stack using a rotating arm. The complete burger is then moved forward to a wrapping station where it is enveloped in printed foil or wax paper. Wrapping is done by folding each side toward the center and then folding the base upward before rolling the package forward. Wrapped burgers are placed into holding bins arranged by product type. Bin trays are heated from beneath with radiant elements to hold temperature. Burger names and identifiers are shown on digital displays above each bin. The wrapped burgers are then pulled in the order of assembly requests from service or drive-through lines. For specialty burgers with additional ingredients, separate modules are added to the line. Bacon is pre-cooked in convection ovens and held on heated trays. Spicy toppings or sauces are dispensed through separate triggers. Extra patties are added by adjusting tray positions to align multiple cooked patties before final topping. The entire burger line is modular and designed for high throughput. Each step, from toasting to wrapping, is timed and paced using conveyor intervals and operator rhythm. Cooked patties are used within a fixed window to maintain thermal properties during assembly. The square patty shape aligns precisely with the round bun through placement guides. Cheese coverage is optimized by placing the slice diagonally across the square patty. Lettuce folds are standardized to reduce overhang and dripping. Tomato slices are inspected visually for diameter and replaced if undersized. Onions are separated into ring layers to maintain consistent thickness. Pickles are spaced to prevent overlap or bunching. Sauce volumes are adjusted using pump restrictors. Each pump cycle delivers a metered dose that is verified weekly by weight checks. Dispense angles ensure center placement with minimal deviation. Top bun pressure is measured periodically to confirm compression does not exceed tolerance. Overcompression can cause lettuce or tomato slippage. Wrap tightness is checked by torsion testing with digital force gauges. Grill platen pressure is balanced to avoid sear marks that penetrate too deeply. Contact time is calibrated to match patty water content and surface heat conductivity. Belt tension is maintained through spring-loaded rollers at both ends of the grill. Drip pan contents are filtered and cooled before disposal. Grease flow is measured to calculate fat loss per batch. Each tray of patties is weighed at intervals to confirm moisture retention and yield. Conveyor speed is set to match maximum output per cook zone. Bun toast time is synchronized to meet grill exit timing. Topping replenishment occurs based on tray weight thresholds detected by load cells. Tomato and onion prep stations are cleaned and reset every few cycles to prevent buildup. Cheese trays are kept below 5 degrees Celsius using chilled gel plates. Lettuce bins are sloped for continuous access without compaction. Burger stacking alignment is controlled by operator training and guided bins. Variants like double burgers use the same assembly line with secondary patty placement after cheese. Burgers with spicy or grilled ingredients use segregated stations to prevent flavor transfer. All process parameters are displayed on line-side screens for real-time monitoring. Operators adjust pump pressure, toast speed, and tray positions based on on-screen instructions. Each station is time-stamped to maintain consistency across shifts. Ingredient freshness is managed by rotation schedules and bin timers. No topping remains in use beyond its designated holding time. Each component has a separate preparation and service life which governs when trays are replaced. The square patty ensures uniform cooking and reduces edge shrinkage. Griddle contact area is maximized by flat pressing. Consistent doneness is achieved across all patties through center-out thermal profiles. The full Wendy's burger is formed by layering precise ingredient units in defined order. Each addition is made at a fixed position along the conveyor. The sequence ensures balance in flavor, weight, and thermal distribution. Assembly line pacing is regulated by burger type, quantity, and order load. Stack height is limited by bun compression threshold. Burgers are finalized within a tight time window to maintain optimal serving temperature. Pizza Hut. Pizza production begins with the preparation of pizza dough using automated high-capacity mixers. Each batch starts with high-protein wheat flour dispensed from overhead silos through a pneumatic conveyor into a stainless steel mixing bowl. Water is metered precisely from a temperature-controlled supply line and delivered into the bowl through solenoid valves. Instant dry yeast is stored in sealed bins and dispensed by auger into the bowl after water. Salt and sugar are pre-weighed and released into the bowl from vibratory feeders mounted above the mixer. Vegetable oil is pumped from a storage tank through a heated line and added last to ensure uniform distribution. The spiral mixer begins in a slow speed mode for 1 minute to hydrate the dry ingredients. After hydration is complete, the mixer shifts to high speed to develop gluten structure. Mixing continues for 8 to 10 minutes until the dough reaches a defined elasticity and target temperature range. The dough is discharged into a trough and transferred to the divider using a hydraulic lift arm. The divider uses a piston system to cut dough into fixed weight portions based on pizza size specifications. Each dough piece is rounded into a ball shape by a rotary rounding mechanism and deposited onto a lightly floured tray. Rounded dough balls are conveyed into a temperature and humidity-controlled proofing cabinet. The proofing stage allows yeast fermentation to produce gas and relax the dough structure. Temperature is held around 38 degrees Celsius and humidity near 85% to maintain surface softness. After proofing for approximately 1 hour, the dough is moved to a pressing station. Each ball is loaded onto a heated platen, which presses the dough into a disc shape. Pressing is done with a hydraulic top plate that flattens the dough to a specified diameter and thickness. Heat from the platen sets the shape and prevents shrinkage during later handling. Pressed dough discs are transferred to perforated baking pans or screens using a vacuum lifter. A light mist of oil is applied to the pan surface to prevent sticking. The dough and pan then move along a conveyor to the topping line. Topping application begins with sauce deposition using a volumetric piston filler. The sauce is pumped from a heated holding tank and dispensed in a spiral pattern starting from the center of the dough. A rotating disc beneath the pizza ensures even coverage without manual spreading. Shredded mozzarella cheese is stored in chilled hoppers and fed to a depositor via a vibratory conveyor. Cheese is distributed through rotating paddles that drop a measured weight evenly across the surface. Cheese coverage is calibrated to stay inside the dough border. Additional toppings are added in a fixed sequence depending on pizza type. Pepperoni slices are dispensed from a rotary carousel that places overlapping slices in concentric rings. Cooked sausage crumbles are metered through a hopper with a gate-controlled release. Vegetable toppings such as mushrooms, green peppers, and onions are added from separate hoppers using calibrated volumetric scoops. Bacon pieces and ham strips are dispensed from compartments, lined with agitators to prevent bridging. Olives are dropped from a chute fitted with a shaker plate to ensure even distribution. Pineapple chunks are added last and drained before dispensing to avoid excess moisture. Each pizza proceeds to the oven loading belt, which is synchronized with baking time and oven speed. The pizzas enter a conveyor oven with a stone or mesh belt and a controlled baking chamber. Top and bottom heat are separately adjustable using electric elements or gas burners. Baking time is generally between 6 and 7 minutes, depending on pizza size and topping load. The oven is divided into thermal zones which apply different temperatures to optimize crust and topping finish. Air circulation fans maintain uniform heat distribution within the chamber. Crust browning is controlled by bottom belt temperature and pan contact. Cheese melt is regulated by top zone intensity. Sauce bubbling and topping cooking are completed within the dwell time set by conveyor speed. Once baking is complete, the pizza exits the oven and is transferred onto a staging table with a heat-resistant surface. A metal lifter is used to remove the pizza from the baking pan if one was used. The pizza is then slid onto a cutting board positioned below a rocker blade cutter. The cutter is hinged to apply uniform downward pressure and is guided by slots in the board to maintain equal slice sizes. Standard cut configurations are 4, 6, or 8 slices depending on diameter. Each pizza is rotated to complete perpendicular cuts if required. Cut pizzas are transferred onto corrugated cardboard discs which serve as a support base. The pizza and disc are inserted into printed boxes by a sliding motion, which prevents topping displacement. Boxes are closed with a fold lock mechanism and stacked in batches on a heated shelf for holding. Specialty pizzas with cheese-stuffed crust use a different pressing process where cheese sticks are inserted into the dough edge before sealing. The dough is crimped mechanically to enclose the cheese along the perimeter. These variants are baked with slightly longer dwell times to ensure cheese softening. Thin crust pizzas skip the proofing stage and are sheeted directly after mixing. The sheeting line flattens dough using a 3-stage roller system that progressively reduces thickness. Sheeted dough is cut to shape using a rotating die and docked to prevent bubbling. It is transferred directly to the topping line without additional rise. Pan pizzas use thicker dough portions which are hand-pressed or machine-pressed into deep pans coated with oil. The oil creates a fried base texture during baking. These pans are baked longer at lower temperatures to prevent surface burning. Pizza Hut production lines are modular and can run multiple styles concurrently by using different lanes. Each lane is fed by a shared dough room and topping prep area. Toppings are staged in mobile chilled carts that are swapped based on menu rotation. Sauce preparation occurs in a separate area where tomato concentrate is blended with water and seasoning. The sauce is cooked in steam kettles and cooled rapidly before being pumped to holding tanks. Cheese is shredded in-house using rotary drum shredders or received pre-shredded in lined totes. Toppings are prepared using a combination of manual and automated methods. Whole vegetables are washed and sliced on rotating blade machines. Meats are pre-cooked and diced using high-speed dicers or crumblers. Toppings are loaded into color-coded bins and inserted into the topping line feed hoppers. Ingredient flow is monitored by load cells under each hopper, which signal refill triggers when weight drops below threshold. Each depositor is linked to a PLC that controls dispense rate, duration, and alignment. Pan and tray washing systems clean and sanitize bakeware after each use. Washed pans return to the pressing line in timed cycles. Conveyor belts are brushed and wiped at shift intervals to remove topping residue. All components of the pizza undergo mass balance verification to ensure recipe compliance. Each pizza's final weight is checked on a dynamic scale before boxing. Deviations trigger visual alerts and operator review. Conveyor speeds, depositor timing, oven temperatures, and cut configurations are all adjustable by touchscreen interfaces mounted on each station. Operators select pre-programmed recipes which load all parameters automatically. The dough formulation is calibrated to yield consistent rise, chew, and browning under standard conditions. Oil content determines tenderness, while yeast quantity controls gas production. Mixing temperature is adjusted based on flour temperature and ambient conditions to ensure batch uniformity. Cheese melt properties are influenced by moisture content and shred size. Sauce consistency affects spreadability and absorption into the dough. Topping order ensures base ingredient contact with heat for proper cooking. Every Pizza Hut pizza follows a defined flow from dough to boxed product. Each process stage adds a functional component that determines structure, flavor, or visual finish. Assembly is done in linear progression with limited manual input beyond topping reload and box stacking. Pizza format changes involve reconfiguring press molds, pan shapes, and depositor settings. Crust variants, such as garlic butter infused or herb seasoned, are handled by adding a post-bake brushing stage, where liquid toppings are sprayed onto the crust using a rotating nozzle arm. Pizzas with drizzle finishes or sauces applied after baking use a dedicated finishing table where squeeze bottle applicators or peristaltic pumps add final ingredients. These finishes are applied before boxing and allowed to set for several seconds. Temperature retention in boxes is enhanced by vent hole design, box material thickness, and stacking method. Pizza integrity during transport is preserved by maintaining alignment and minimizing topping shift through controlled insertion angles. The industrial process of bread production begins not with baking, but with an orchestrated balance of mechanics and chemistry, where every gram of input is measured, every rotation of a blade is timed, and every degree of heat is calculated long before the first loaf begins to take shape. The cycle starts in the mixing room, where automated ingredient handling systems transport vast quantities of flour through pneumatic conveyors, drawing it from silos positioned outside the facility and funneling it in clouds of fine white powder into stainless steel batch hoppers that feed into the primary dough mixers. These mixers, towering and gear-driven, don't simply stir. They press, fold, and stretch the mixture with rotating arms that mimic the pressure and pull of hands, but at a scale and speed no human could replicate. At the moment liquid meets dry, the system kicks into life, and the rhythm of kneading begins. Inside the mixing chamber, every second counts. The speed starts slow to allow hydration, gradually increasing as gluten strands form and interlace, building the elastic structure that will define the shape, rise, and texture of the finished bread. Temperature sensors within the dough track the frictional heat produced during mixing, while torque sensors monitor resistance to ensure the dough reaches a consistent development profile. Cooling jackets around the mixer basin activate if necessary, keeping the dough within its ideal thermal range to avoid overproofing later in the process. Once the target consistency and elasticity are reached, soft, slightly tacky, extensible, but resilient, the dough exits the mixer through a bottom hatch, sliding as one heavy, cohesive mass into the next stage. A sheeter receives the dough next. Twin rollers compress it into a continuous slab, which then moves through a series of gauges to ensure thickness and density remain exact. This is not a shaping step, it's preparation. The flattened dough is directed into a high-capacity divider, where a series of volumetric pistons cut the slab into uniform portions. These pistons measure by volume rather than weight, ensuring that even as humidity or temperature fluctuates slightly, each piece contains the exact same mass of air and dough combined. Once divided, the pieces are dropped into intermediate proofers, tall, climate-controlled chambers where the dough rests in a carefully maintained environment of warmth and humidity. It's here that the dough begins to ferment actively for the first time. The yeast, having been activated during mixing, releases carbon dioxide, expanding the structure from within. But this step isn't about final rise. It's about conditioning the dough, allowing it to relax after the physical stress of division so it can be molded without tearing. After a set number of minutes, each portion travels via conveyor to the molder. A set of guide rollers gently flattens the dough again. Then curling belts begin to shape it, rolling the mass inward to form a tight spiral that will become the loaf's interior structure. Pressure plates calibrate tension precisely, ensuring the outer skin of the dough wraps around the inner layers tightly enough to support rise, but not so tight that the loaf bursts during baking. Once molded, the loaves drop gently into metal baking pans, moving along a wide belt. Each pan is pre-lubricated with a fine mist of oil dispensed by a jet spray system to ensure clean release after baking. At this point, the pans pass through the final proofer, a long, enclosed tunnel where heat and humidity are kept within strict boundaries. Here, the loaves experience their final rise, swelling as fermentation accelerates. The gases trapped in the dough expand, the gluten matrix stretches to accommodate the volume, and the surface tension pulls tight, smoothing the top into a rounded dome. Sensors along the proofer track height, spacing, and proofing time. Any variation is logged, and the system will adjust conveyor speed or proofer climate to compensate. If the dough rises too quickly, the texture becomes irregular. Too slowly, and the crust may blister or fail to color evenly. Timing here is crucial. Baking must happen at the peak of fermentation activity to lock in that volume. Once the proofing cycle finishes, the pans emerge from the chamber and feed directly into the oven. The industrial oven is a continuous tunnel design, divided into multiple thermal zones with independent top and bottom heat controls. As the pans enter, steam injectors release a high-pressure burst across the loaf tops. This initial moisture keeps the crust soft in the early minutes, allowing for maximum oven spring as the bread expands rapidly under intense heat. The steam also sets the crust structure and eventually contributes to its color and gloss. The baking process unfolds in stages. First comes expansion, where gases expand, alcohols evaporate, and enzymes break down residual sugars. Then comes gelatinization, as starches swell and set. Finally, Maillard reactions begin on the surface, turning the pale, supple dough into a rich, caramel-toned crust. The belt moves at a steady pace, calibrated so that by the time each loaf exits the last zone, it has reached the exact internal temperature required for complete bake, usually just over 96 degrees at the core. Exiting the oven, the loaves are hot and fragrant, but far too fragile for packaging. They roll forward on the conveyor and enter a spiral cooling system, a towering structure of coiled belts that winds upward, allowing the loaves to circulate through cooler air over the course of 30 to 40 minutes. Fans direct airflow from multiple angles, and vents above the line extract excess humidity to avoid condensation forming on the crust. As the temperature gradually drops, the crumb sets fully and moisture redistributes inside the loaf, ensuring softness remains throughout shelf life. Once cooled, the pans reach the depanning machine. A rotating arm, fitted with suction cups, lifts each loaf upward with precision timing, placing it onto a transfer belt while the empty pan continues onto a cleaning line. The pans are scrubbed with mechanical brushes, sprayed with sanitizer, and then dried by air knives before being stacked or returned to the molder for the next round. Meanwhile, the bare loaves now advance towards slicing and packaging. If the bread is destined for sale as whole loaves, it bypasses this stage, but most continue on to the slicer. This machine is built for speed. Multiple blades, mounted vertically in a row, oscillate at high speed as each loaf is pushed through by a belt-driven ram. The slices fall into alignment instantly, held together by guide rails as they move forward still in loaf shape. The next step is bagging. A plastic bag is blown open by a quick burst of air and guided into place by forming horns. The sliced loaf drops in, and a closing device, either a twist tie, tamper band, or plastic clip, seals the bag in one motion. An inline printer stamps each bag with a code indicating date, time, production line, and batch number. The sealed loaf is then guided onto a secondary conveyor for inspection. Cameras and weight sensors scan every packaged loaf. Any irregularities in size, shape, color, bag print, or closure are instantly flagged. Rejected loaves are diverted automatically, while the accepted product continues forward to be grouped for carton packing. Robotic arms pick up loaves in sets and stack them into shipping boxes, which are then sealed, labeled, and passed to the palletizer. The palletizing system uses multi-axis robotic arms to stack cartons onto wooden pallets in precise formations designed to prevent shifting or damage in transport. Slip sheets are placed between layers for stability. Once full, the pallet enters a stretch wrapper, where plastic film binds the load tight from base to top. A printed label is applied to the outer edge of the film, detailing product information, origin, destination, and tracking codes. Every action in this process is overseen by a centralized control network that connects mixers, dividers, molders, ovens, coolers, and packers into one coordinated line. Data flows constantly between stations. If the divider senses a shift in dough density, the molder adjusts tension. If the oven reports inconsistent browning, the slicer slows slightly to sync packaging output. Everything is in motion, yet everything is balanced. In a large-scale factory dedicated to the continuous assembly of sandwiches, every stage is a precisely engineered operation where timing, alignment, and consistency converge across hundreds of feet of synchronized machinery. And the process begins long before the first sandwich reaches the wrapper. It starts with bread loaves, already baked, cooled, and brought into the slicing system in racks, where they are automatically depanned, aligned, and fed into high-speed slicers fitted with ultra-sharp, serrated, or ultrasonic blades that oscillate thousands of times per second to deliver uniform, clean-edge slices without compressing the soft interior crumb or fracturing the crust. Once sliced, the bread slices travel by conveyor to a pre-alignment station, where camera-guided sensors and rotating guide arms ensure every slice is positioned in the exact orientation required for the next phase, which is the laying down of the base slices. These are distributed in pairs or rows, depending on whether the line is configured for single or multiple sandwich formats, and set evenly onto the moving belt with equal spacing between each set. The flow is constant, with no interruption between batches, and any variation in slice thickness or alignment is corrected in real time by pneumatic actuators and servo-driven guides that subtly adjust position and speed without halting the line. As the bottom slices approach the filling zones, the first application arrives in the form of spread, be it mayonnaise, mustard, aioli, butter, or any other emulsified or creamy base. A series of nozzles or roller spreaders applies a controlled layer, often using pulse pressure, to shoot a fan of spread across the surface, which is then evened out by a soft-tipped roller or oscillating blade to ensure consistent coverage all the way to the edges of the bread. Sensors mounted above each lane scan the surface to confirm the presence, distribution, and thickness of the spread. And if coverage falls below specification, a feedback loop either reapplies the layer or removes the sandwich from the line. After the base layer is applied, the sandwich moves into the protein zone. Here, pre-sliced meats such as turkey, ham, beef, chicken, or plant-based alternatives arrive from upstream feed systems, where they have been portioned, weighed, and fanned into stacks by centrifugal feeders or vibratory shakers. These stacks are lifted by robotic pick-and-place arms equipped with vacuum suction or gripper fingers, depending on the product's texture, and laid gently onto each bread base with alignment controlled by high-speed imaging systems that adjust position in real time to match the orientation of the incoming slice. Every portion is weighed by inline check weighers before being applied, ensuring that each sandwich receives a uniform protein layer, with rejections happening instantly and automatically if tolerances are exceeded. Next comes the cheese layer, which moves from chilled stacks through a peeling and singulation system that separates individual slices, removes any protective film, and transfers them to a placement module. The cheese is picked and placed onto the meat with exact positioning, sometimes staggered depending on the sandwich style, and lightly pressed to ensure it conforms to the underlying surface without folding or hanging over the edge. The equipment adjusts for slice fragility using low-pressure vacuum heads and static control to prevent light cheeses from sticking to conveyors or deforming during placement. Vegetables come next, and this stage is often the most complex due to the variability in size, moisture, and fragility of the ingredients. Lettuce is dispensed from overhead hoppers with calibrated vibratory trays that gently shake shredded or leaf lettuce onto the sandwiches in measured volume, distributed evenly by spinning diffusers that sweep across the width of the belt. Tomatoes, cucumbers, and other sliced produce are fed from rotary magazines that release single slices in sequence, timed to the belt's movement, so each tomato lands directly at the center of the sandwich, guided by small airflow puffs or mechanical nudges if needed. Onion rings and other light layers are dispensed from spiral feeders or drop chutes, often with the assistance of static eliminators and light misting systems that prevent separation or clumping as the vegetables fall into place. If the top slice requires its own spread or condiment layer, a mirrored version of the first spreading station appears here, applying the layer just moments before the slice is joined to the assembled base. The top slice is picked by robotic arms from a secondary line of aligned bread slices, flipped if necessary depending on crust orientation, and gently pressed onto the assembled sandwich with just enough force to compress the stack into a unified structure without squeezing out fillings or deforming the shape. At this stage, the sandwich enters the compression and forming section. A series of soft rollers or belt presses applies uniform downward pressure to stabilize the build, enhance bite adhesion, and ensure the sandwich holds together through slicing, wrapping, and handling. The compression rollers are timed precisely to match belt speed, and the pressure profile is tuned to the product type, with more delicate sandwiches receiving lighter contact and denser builds compressed more firmly to lock the layers in place. Now fully assembled, the sandwich proceeds to the slicing station, where high-speed rotary or ultrasonic blades divide the product into the desired shape, typically halves or triangles. The slicing system is mounted on actuators that follow the motion of the sandwich as it moves along the belt, ensuring the blade enters and exits the loaf cleanly without tearing or pulling. Blade tension, sharpness, and angle are maintained through automated diagnostics, and the entire slicing module is flushed and sanitized between shifts to prevent cross-contamination. Cut sandwiches are now directed into the inspection lane, where overhead cameras and weight sensors verify slice alignment, edge definition, symmetry, and overall appearance. If a sandwich is misaligned, overfilled, underweight, or damaged during slicing, it is ejected by air blast or mechanical diverter before it reaches the wrapping system. The accepted sandwiches pass into the packaging zone, where the method of wrapping depends on the product's end use. For flow-wrapped sandwiches, the product enters a film feed tunnel where printed plastic film is drawn over and around the sandwich by guide belts, sealed along the back and ends by heated jaws that press and crimp the film closed in less than a second. A date coder prints production information onto the film surface just before the end seal. For chilled sandwiches sold in wedges or clamshells, the product is inserted by pick-and-place units into pre-formed rigid plastic containers. The lid is pressed or snapped into place and sealed with adhesive label strips or heat-sealed foil, depending on product design. Transparent sections are aligned with the sandwich face to ensure maximum visibility on shelf. Once wrapped, the sandwiches are grouped for boxing. A case packer counts the products and loads them into corrugated cartons, aligning each stack for minimal movement during shipping. Cartons are formed automatically from flat blanks fed into a forming station, sealed with hot melt glue or folded tabs, and labeled on the fly with barcodes, lot numbers, and shipping data. Each carton is scanned and weighed, and any deviation is flagged for inspection. The approved boxes move to the palletizing cell, where robotic arms stack them onto wooden or plastic pallets with layer patterns designed to balance weight and prevent shifting. The pallets are then rotated through a stretch wrapping station where film is applied under tension from bottom to top, stabilizing the entire load for transport. A final label is printed and applied to the side of the pallet with a scanner-readable code containing the production batch, shift, line number, and timestamp. Bagel production at factory scale is a continuous ballet of movement and transformation, where the dense, chewy character of each finished product is the result of precisely sequenced operations carried out by synchronized machines, each tuned to interact with dough in a way that preserves its integrity, develops its structure, and creates the exact conditions required for that unmistakable crust and crumb. It all begins in the dough room, where flour moves from towering silos into enclosed conveyor tubes, descending by weight into a batcher that draws measured volumes of water, salt solution, yeast suspension, and additional agents through chilled, jacketed feed lines that maintain temperature consistency from the first pump to the final discharge into the mixer. As the ingredients come together in a high-capacity spiral mixer, the arms begin turning slowly, cutting through the thickening mass with powerful, spiraling force, pulling the flour into the water and folding the developing dough inward from all angles. Unlike lighter breads, bagel dough requires far more resistance and strength, so the machines are set to operate under heavier torque, and the texture is intentionally firmer from the start. Temperature probes track internal friction heat. If the dough rises beyond the target, a cooling system kicks in, circulating chilled water through the ball's outer jacket, allowing the dough to strengthen and ferment without overheating. The mixing continues until the dough becomes tight, elastic, and resilient to touch, ready not for shaping, but for division. At this point, the dense dough is released through a bottom hatch and fed directly into a portioning unit that slices it into thick, consistent strips, each one calibrated for weight and volume by servo-guided sensors that track the length, width, and compression of the dough strand as it moves forward on the belt. These portions are then carried forward to the bagel former, a specialized system unique to this category of baked goods. Here, each dough piece is rolled into a rope between two textured conveyor belts, gradually tapering the ends for seamless closure. The ropes are then transferred to the forming drum, a rotating cylinder fitted with a center plunger and an outer ring guide that picks up the rope, curls it into a circle, and presses the ends together into a seamless loop without pinching, tearing, or folding. Formed bagels are deposited onto a wide, dusted conveyor belt, each one spaced perfectly from the next by indexing arms that keep rows uniform as they head toward the proofing section. At this stage, the dough is still dense and compact and needs controlled time to relax and ferment before any further processing. The trays of raw bagels enter an enclosed, temperature and humidity regulated proofer where warm, moist air surrounds the dough, gently encouraging expansion without aggressive rise. Over the next 15 to 20 minutes, the yeast becomes active, releasing carbon dioxide and creating a subtle softness beneath the taut exterior. Proofing times are controlled to the minute, with sensors tracking volume gain and relative humidity in every lane of the chamber, so that every bagel arrives at the next step with the same bounce, shape, and tension. What follows is the defining characteristic of bagel production: boiling, or more accurately, a high-temperature water bath that sets the outer crust before baking begins. As the proofed bagels exit the chamber, they move onto a boiling belt that carries them through a long stainless steel trough filled with circulating water, often mixed with barley malt or a similar solution to enhance browning later in the oven. The bagels float as they enter, and a set of rotating paddles gently submerge each one to ensure even exposure. They spend only seconds in this bath, but it's enough to gelatinize the starches on the surface, locking in shape and creating the foundation for that dense, glossy crust. Once boiled, the bagels are lifted from the water by an upward-sloping mesh belt and allowed to drain momentarily before entering the topping section, where optional finishes, sesame, poppy, onion, salt, are applied. This happens through a combination of timing, moisture, and gravity. The wet surface of each bagel acts as a natural adhesive, so as they pass under overhead hoppers or through rotary topping applicators, the seeds or seasonings fall onto the dough and stick cleanly to the surface. Excess toppings are collected by a vibrating reclaim system beneath the belt, filtered and returned to the hopper for reuse, ensuring nothing is wasted and every bagel receives an even coating. The topping section leads directly into the oven, a massive tunnel-style system divided into multiple thermal zones that gradually bring the bagels from boiled to baked over the course of 10 to 12 minutes. The first zone introduces radiant heat to activate oven spring, but because the crust is already partially set, expansion is modest and the shape remains tight and uniform. In the middle zone, the crust begins to brown, driven by Maillard reactions that create the deep caramel tones and toasty aroma typical of well-baked bagels. The final zone balances color and internal moisture, holding a slightly lower heat to allow the core temperature to rise without burning the toppings. Throughout the bake, airflow is precisely directed and humidity is adjusted by steam injection valves to control crust thickness and finish. As they exit the oven, the bagels are fully formed, firm to the touch, richly colored, with a light sheen from the boiling stage and a tightly structured crumb inside. But at this point, they're still over 90 degrees Celsius internally and too hot for packaging, so the belt carries them into a spiral, cooling tower, a towering column of coiled belt that winds upward, allowing each bagel to travel along a rising path while being cooled by ambient air and filtered ventilation. Over the next 20 to 30 minutes, the internal temperature drops steadily and the crust stabilizes, preventing condensation and preserving the chewy exterior texture. From the base of the spiral, bagels are sorted by product type: plain, topped, seeded, and diverted into corresponding packaging lanes. If they are to be sold whole, they continue uncut, passing through alignment rails and into flow wrapping tunnels, where printed film encloses them in a tight, sealed wrap that's closed by heat-sealed seams on the underside. For multi-packs, bagels are counted and stacked automatically, transferred into trays or bags using pneumatic plungers or robotic suction heads, and sealed with clips, twist ties, or tamper-proof labels. Batch codes, production times, and expiration dates are printed by inline thermal inkjet systems on the package surface. If the bagels are destined for pre-sliced use, they proceed to the slicing unit, where a high-speed circular blade, often with ultrasonic vibration, cuts horizontally through each bagel's midpoint, while the product is held firmly in a compression cradle that prevents movement or tear out. The two halves remain paired and are then rewrapped as a sliced unit, ready for sandwich use or toasting. The sliced bagels are also inspected by weight, diameter, and color, with overhead cameras tracking any deviation in cut depth or alignment and removing out-of-spec product instantly from the conveyor. From there, the finished and packaged bagels are transferred into carton loading stations. A mechanical arm stacks them into pre-formed boxes, which are then sealed, labeled, and conveyed to the palletizing zone. Here, a robotic palletizer organizes the cartons in tight formations, applying slip sheets between layers and wrapping each pallet in film to protect it during transport. Each pallet is labeled with a scannable tracking code that contains all relevant production data: time, line, operator, batch, and destination. Throughout this entire process, every machine, every transfer, and every transformation is governed by a central control system that monitors line speed, batch integrity, ingredient flow, humidity, oven temperature, belt timing, and packaging rates. Adjustments happen automatically. If the boiling water cools by 2 degrees, the belt speed slows. If the oven heat drifts too high in zone 3, airflow is redirected. If the topping adhesion falls below threshold, an alert is triggered, and the hopper motor pulses slightly to shake more seed onto the line. Nothing here is guesswork. Everything is calculated. Bagels don't just bake. They're shaped, built, boiled, and finished by systems that never stop watching, adjusting, and maintaining perfect rhythm. The machines don't work alone, but in coordinated layers, each one tuned to preserve the dense structure, glossy crust, and unmistakable bite that defines a factory-made bagel. In just over an hour, a lump of flour and water is transformed into something firm, chewy, finished, and sealed, ready to ship, ready to slice, ready to toast, and repeated thousands of times per hour without pause. Oreo wafer rolls are produced using a dual-stream manufacturing process involving continuous wafer sheet production and separate cream filling preparation, which are later synchronized through an automated integration line. The raw materials for the wafer component are dosed automatically from bulk silos into individual weighing hoppers. The base formulation consists of low-protein wheat flour, high-fat alkalized cocoa powder, refined sucrose, leavening agents, salt, water, and a controlled amount of oil-based emulsifiers. Dry ingredients are metered into a high-capacity horizontal mixer with dual-axis paddles designed for uniform blending. Liquids are injected through precision nozzles mounted at the top of the mixing chamber. The total mixing cycle is programmed between 6 and 8 minutes at varying RPMs, first for dry distribution, then for incorporation of wet components. Dough temperature is maintained between 22 and 26 degrees Celsius. Moisture content is monitored via inline near-infrared sensors and must fall within 10.0 to 11.5% before release to the forming line. Dough is transferred via a covered screw conveyor to a pre-sheeting station. Here, a primary roller flattens the dough into a rough sheet approximately 5 mm thick, which then feeds into a 3-stage reduction system. Each stage includes a pair of high-precision, counter-rotating steel rollers with micrometric gap control that sequentially reduce the dough thickness to 1.2 pounds. Dough tension is maintained using differential speed rollers to avoid tearing. Edges are trimmed continuously using rotary cutters, and trimmings are conveyed pneumatically back to the pre-mix hopper for reintegration. The thin dough sheet enters a continuous baking tunnel consisting of 8 to 12 independently controlled zones. Heating is achieved via direct gas-fired convection and radiant ceramic panels. Internal zone temperatures range from 180 to 220 degrees Celsius depending on the position. Air velocity, humidity, and conveyor speed are continuously adjusted via PID feedback loops. Total bake time is between 85 and 105 seconds. Baked sheets are discharged onto a mesh cooling belt, where ambient forced air coolers reduce sheet temperature to below 30 degrees Celsius within 90 seconds. Cooling is followed by longitudinal slitting. Circular slitting blades mounted on adjustable shafts divide the wide wafer sheet into narrow, uniform ribbons matching the final roll width. Slitting accuracy is maintained using laser alignment sensors. Each ribbon is immediately guided into a spiral roll-forming station equipped with a rotating mandrel. A servo-controlled drum pulls the ribbon over the mandrel, while controlled tension and heat reactivation of the dough surface allows the strip to roll into a rigid, cylindrical shell. Formed rolls are passed through a stabilization tunnel maintained at 65-75 degrees Celsius with low humidity to fully set their shape. Rolls are discharged onto a buffer conveyor which feeds into the cream filling station. In parallel, the cream filling is prepared from sugar, hydrogenated vegetable oil, milk solids, lecithin, artificial flavor, and small amounts of stabilizers. Ingredients are batch loaded into a jacketed mixing vessel with shear blades rotating at 1400 and 1600 RPM. Oil is added slowly to prevent separation, and the entire mixture is heated to 45-48 degrees Celsius. Mixing continues for 10 to 15 minutes until a homogeneous emulsion is achieved. The finished cream is transferred through insulated stainless steel pipes to pressurized holding tanks. Agitators maintain cream fluidity and prevent phase separation. The filling is then pumped to multiple servo-driven depositors aligned with each lane of the wafer roll conveyor. Each nozzle delivers a calibrated cream column into the core of each roll, with filling weights accurate to plus 0.2 grams. The nozzle retracts dynamically during deposit to ensure central cream alignment and full core penetration. Cream-filled rolls pass through a secondary cooling tunnel set to 10 degrees Celsius for 60 seconds to solidify the filling. Thermal imaging sensors confirm internal stabilization before exiting. At this stage, each roll is individually scanned for dimensional conformity, surface defects, and fill anomalies. Rolls not meeting target criteria for weight, symmetry, or visible cream containment are diverted via pneumatic actuators into separate waste chutes. Approved rolls proceed to flow wrapping. Individual rolls are aligned using vibratory feeders and grouped into packaging sets based on SKU configuration. Film is dispensed from reels and formed into tubes by collaring mechanisms. Horizontal seal jaws apply pressure and heat at 135-145 degrees Celsius for 0.3 to 0.5 seconds to close the ends and seal the longitudinal seam. Nitrogen gas is flushed into the package before sealing to displace oxygen and slow fat oxidation. Each wrapper is printed with batch code, timestamp, and best before date using thermal inkjet printers synchronized with the machine cycle. Wrapped products are conveyed to a cartoning unit, where robotic arms pick and place the flow-wrapped units into pre-formed cartons. Cartons are constructed from pre-creased flat blanks that are folded and glued using hot melt adhesive. Carton fill confirmation is performed using weight sensors and machine vision. Completed cartons are sealed, labeled, and aggregated into corrugated shipper boxes. Each shipper box is barcoded for traceability and palletized in accordance with standard load configurations. Palletized loads are stretch-wrapped and transferred to climate-controlled warehouse storage. Storage areas maintain relative humidity below 60% and ambient temperature between 18 and 22 degrees Celsius to prevent wafer degradation and cream migration. Inventory turnover is managed via FIFO principles enforced by warehouse management software, which integrates with factory MES and ERP systems for batch tracking. Process validation occurs every production shift. Operators test dough rheology, sheet thickness, baking curve, moisture content, cream viscosity, deposit weight, roll hardness, and package seal integrity. Data is recorded in the batch record along with any machine adjustments or anomalies. All critical control points, including cream deposit temperature, bake time, and packaging seal strength, are electronically logged and must fall within specification limits or trigger corrective action. Cleaning in place procedures are scheduled every 8 to 12 hours. Cream lines are flushed with heated water, followed by alkaline detergent, acid rinse, and sterile water rinse. Wafer production lines use dry cleaning methods for rollers and belts, followed by compressed air cleaning and manual wipe down of forming mandrels. Swab testing is used to verify microbial cleanliness, and ATP bioluminescence testing is used to assess organic residue. Production yield is calculated by comparing in-feed material weight to packaged product weight, adjusted for expected waste. All off-spec rolls, excess cream, and packaging rejects are weighed and categorized into waste type. Cream residue is routed into closed collection tanks for food waste processing, while wafer rejects are disposed of according to facility-specific food waste handling protocols. All mechanical systems, mixers, sheeters, formers, depositors, and sealers are maintained under a scheduled preventive maintenance program. Bearings, blades, nozzles, and conveyors are inspected and replaced based on run hours. PLC logic controllers monitor machine health via vibration sensors, motor load curves, and cycle time deviation analysis. Batch documentation includes raw material lot numbers, machine settings, environmental conditions, operator identification, in-process test results, and any deviations from standard operating conditions. These records are archived digitally and are subject to internal audits, third-party verification, and regulatory inspection. Full traceability is retained for every unit produced. Nutella B-Ready consists of 3 major components manufactured on synchronized but separate production lines: a wafer shell, a Nutella filling, and the final packaging. Each component is produced under tightly controlled parameters using fully automated equipment integrated into a high-throughput, continuous processing line. The outer shell is made from a low-moisture, wheat-based dough formulated to bake into a crisp, blister-free wafer. The dough formulation begins with dosing refined wheat flour, sugar, salt, leavening agents, and a blend of plant-based fats into an enclosed paddle mixer. Dry ingredients are dispensed from silo systems into individual weigh hoppers with accuracy to within plus 0.1%. Liquids, including water and emulsifiers, are metered from heated tanks using flow meters. The mixer operates at multiple speeds for uniform hydration and structural development. Once the dough reaches the required consistency, typically between 22% and 25% moisture content, it is discharged via bottom gate valves into an auger conveyor leading to the forming line. The dough passes through a series of lamination rollers where it is flattened to a precise thickness of 1.4 millimeters. Differential speed control across rollers prevents tearing and ensures uniform surface tension. Edge trimmings are continuously recycled to minimize waste and maintain dimensional consistency. The laminated sheet enters a rotary molding system. This consists of a rotating die roller with cavity molds shaped to match the profile of the Nutella B-Ready shell. The dough is pressed into the molds using counter-rotating pressure rollers. An adjustable doctor blade removes excess dough from the roller surface. Molded wafers are transferred via a vacuum pickup system to a baking mesh conveyor, which passes through a tunnel oven with multiple independently controlled zones. The oven zones maintain specific temperature gradients between 180 degrees and 220 degrees, optimized for water evaporation, structural hardening, and color development. Each zone's airflow is modulated by variable frequency drive fans to control browning without burning. Baking duration is typically between 80 and 110 seconds. Thermocouples and moisture sensors measure real-time parameters. Upon exiting, wafers are cooled in line using ambient air-blown axial fans, reducing temperature to under 30 degrees Celsius within 2 minutes. Simultaneously, Nutella filling is prepared in a separate processing room. using a continuous mixing system. Ingredients including refined sugar, vegetable oil, skimmed milk powder, cocoa, and hazelnut paste are dosed using mass flow meters and pneumatic transfer lines. Mixing occurs in a double-jacketed emulsification vessel with counter-rotating impellers operating at 800 to 1200 RPM. The temperature is held between 40 degrees and 45 degrees C during mixing to maintain fluidity and preserve emulsion stability. The finished Nutella filling is pumped through heat-insulated stainless steel piping into buffer tanks connected to multi-head depositor units. These depositors are aligned with the conveyor lanes carrying the pre-formed wafer shells. Each depositor nozzle dispenses a precise amount of filling, usually between 12 and 16 grams, into the hollow cavity of each wafer. Fill weight is monitored using inline load sensors that reject any units outside the tolerance band of plus 0.3 grams. To prevent air entrapment during deposition, the filling nozzle retracts during injection at a synchronized rate, matching the filling viscosity and back pressure. Cream flow is assisted by low-pressure nitrogen to maintain a consistent stream and eliminate pulsing. After filling, each shell passes through a cooling tunnel maintained at 10 to 12 degrees to solidify the fat phase of the filling and prevent oil migration into the wafer wall. Following cooling, a pre-molded wafer lid is applied to seal each filled shell. These lids are formed from the same dough and are baked separately on a synchronized rotary system. A robotic arm equipped with vacuum suction cups picks and places each lid onto the open cavity. An edible adhesive compound, typically a glucose-based syrup, is applied to the perimeter edge to create a bond. Pressure rollers compress the lid and base together for mechanical adhesion. After sealing, each unit passes through a mechanical inspection station. High-speed cameras and laser profilometers verify shell integrity, alignment, lid placement, and overall dimensions. Any product with cracks, offset seals, or excessive height deviation is automatically rejected via pneumatic diverter arms. Approved units move into the packaging preparation line. Packaging begins with flow wrapping. Individual Nutella B-Ready units are spaced on timing belts and fed into the wrapping machine using servo motor controlled pushers. Wrapping film is fed from a roll and formed around each unit via a forming collar. Horizontal and vertical seals are applied using heated sealing jaws that operate at 130 degrees, 145 degrees. Modified atmosphere packaging is implemented via nitrogen gas injection prior to sealing to displace oxygen and extend shelf life. Each flow-wrapped unit is scanned by barcode readers and printed with date codes and traceability numbers using thermal inkjet printers. Units are counted and grouped into sets of 6 or more, depending on market configuration. Grouping is performed using star wheel collators, which align the units into rows for secondary packaging. Secondary packaging uses flat fold cartons erected via vacuum cup pick-and-place systems. Hot melt glue is applied via nozzles to predefined folding flaps, which are pressed closed by mechanical arms. Each carton receives printed labels containing product name, nutritional data, batch code, allergen information, and certification marks. Cartons are weighed for content verification and stacked into larger corrugated shipping boxes using layer-forming robotic packers. Palletizing is performed by 6-axis robotic arms with end effectors designed to grip multiple boxes per cycle. Standard Euro or industrial pallets are loaded based on customer logistics requirements. Pallet patterns are configured to ensure structural stability and airflow clearance. Once loaded, pallets are wrapped using stretch film machines that apply 250% pre-stretched film to secure load integrity during transit. Each pallet is tagged with a pallet license plate containing full production metadata, including line number, production date, shift code, storage conditions, and destination route. Pallets are moved into finished goods, storage warehouses with temperature and humidity control systems set to maintain between 18 degrees Celsius and 20 degrees Celsius, with relative humidity under 60%. Pallet positions are recorded using warehouse management systems with RFID scanners and barcode tracking. Throughout the production process, all inputs, outputs, and in-process conditions are monitored by a centralized SCADA system. Parameters such as oven temperature, mixer torque, depositor cycle counts, wrapping seal integrity, and product rejection rates are logged and archived. Alerts are generated automatically for any deviation outside programmed thresholds. Operators access these systems via HMI touchscreens placed at each station. Sanitation protocols are applied on a rotating schedule. Dough preparation lines are cleaned with dry brushing, followed by ethanol-based surface wipes. Cream handling equipment undergoes full CIP cycles involving alkaline wash, acid rinse, and sterile water flush, validated with conductivity and pH sensors. Wrapping and cartoning stations are cleaned with compressed air, brush downs, and isopropyl surface sanitizers. Swab samples are taken post-cleaning and tested for microbial load. Preventive maintenance is performed weekly on all forming dies, depositor heads, conveyor bearings, and sealing modules. Wear components are replaced based on run-hour tracking. Calibration is conducted daily on dosing equipment, weighing scales, and thermocouples. All calibration records are maintained in compliance with regulatory documentation standards. Product testing occurs hourly. Samples are collected from each production lane and evaluated for weight, length, height, filling content, shell texture, seal strength, and packaging tightness. Sensory analysis includes bite resistance, shell-to-filling ratio, and flavor consistency. Non-conforming samples trigger root cause investigations documented in deviation reports. The entire Nutella B-Ready manufacturing process is standardized to allow for duplication across multiple production facilities with identical output quality. Parameters are optimized to prevent moisture migration, mechanical breakage, and oil separation, which are common defects in filled wafer-based snack formats. Final product shelf life is tested under accelerated and ambient conditions to verify packaging efficacy. Chips Ahoy. Cookie manufacturing begins with bulk ingredient handling systems that store raw materials in separate silos or intermediate bins under controlled conditions. Low moisture, fine milled wheat flour is pneumatically conveyed from outdoor silos into batch weigh hoppers located above the main mixing area. Granulated sugar, brown sugar, cocoa solids, salt, and baking soda are stored in indoor silos or gravity-fed bins and fed into weigh stations using screw feeders with plus 0.1% dosing precision. Vegetable shortening and liquid invert sugar are stored in stainless steel jacketed tanks with continuous recirculation to prevent phase separation. The shortening is heated to maintain fluidity at 45 to 50 degrees Celsius, and the invert sugar is pumped at a constant rate through positive displacement pumps. All liquid and dry ingredients are tracked using an integrated batching control system that verifies real-time mass flow and batch integrity using load cells and flow meters. Each batch is loaded into a planetary batch mixer with a dual paddle agitator system. Mixing follows a 3-stage time-controlled sequence. First, creaming of shortening and sugars is performed for 3 to 4 minutes at low speed. Next, flour and leavening agents are incorporated at medium speed for an additional 3 minutes. Finally, the mixture is scraped down and mixed on high speed for 1 to 2 minutes until a homogeneous dough with uniform texture and target moisture content of 18 to 20% is achieved. Temperature sensors monitor the dough throughout mixing to ensure it remains within the 20 to 24 degrees Celsius range. Overheating is prevented by jacketed cooling systems circulating chilled glycol solution. Once the dough is fully mixed, it is discharged into a stainless steel hopper that feeds a cookie depositor via auger conveyors. Before entering the depositor, chocolate chips are metered into the dough using volumetric feeders to achieve a distribution ratio of approximately 20% by weight. The cookie depositor uses servo-controlled pistons to extrude uniform dough portions directly onto a continuously moving Teflon-coated oven band. Deposit weight per cookie is calibrated to between 18 and 21 grams, depending on SKU. Deposited dough pieces are spaced using optical sensors to maintain consistent center-to-center distance and allow for uniform spread during baking. Each dough piece is flattened slightly by a roller to control shape retention. The baking oven is a hybrid convection and radiant tunnel oven with multiple independently controlled heating zones. Total bake time is typically between 8 and 11 minutes. The oven band runs at a set speed that is continuously adjusted by a PID controller based on real-time surface temperature and humidity readings. Oven zone temperatures range from 160 degrees Celsius in early zones to up to 210 degrees Celsius in final zones to ensure progressive starch gelatinization, moisture evaporation, Maillard reaction, and fat migration. Cookies are monitored during baking using infrared pyrometers that measure surface temperature. Steam injection systems in early oven zones are optionally used to control surface moisture and prevent excessive cracking. Exhaust fans in later zones remove excess humidity and volatile compounds. By the time cookies exit the oven, internal moisture content is reduced to between 3 and 5%, ensuring shelf-stable texture and microbial safety. Upon exiting the oven, cookies are transferred onto a wire mesh cooling conveyor system. Ambient air is directed from below and above the belt using axial fans to achieve uniform cooling to under 30 degrees Celsius in less than 3 minutes. Sensors at the end of the cooling belt check surface temperature before transferring cookies to the inspection area. Conveyor vibrations are minimized to prevent cookie breakage during transfer. Each cookie passes under a vision inspection system equipped with high-resolution cameras and infrared lighting. Software algorithms evaluate cookie shape, surface cracking, chip dispersion, color uniformity, and diameter tolerance. Any cookies failing to meet visual standards are rejected using high-speed air jets. All rejected cookies are weighed, logged, and diverted to waste bins for offline handling. Approved cookies move to the packaging station via a system of vibratory conveyors that align and group the cookies into required configurations. For multi-pack packaging, cookies are grouped into stacks using rotary collators and staged for wrapping. Individual flow packs are created using horizontal form-fill-seal machines. Film is pulled from rolls, shaped around each cookie group, and sealed using heated crimp jaws operating at 130 to 150 degrees Celsius. Modified atmosphere packaging may be used with nitrogen flushing to reduce oxygen and delay lipid oxidation. Each wrapped package receives a printed date code, batch code, and line identification number using thermal inkjet printers synchronized with the conveyor belt. Packages are weighed on inline check weighers with rejection arms for any unit falling outside of mass tolerances. Wrapped units are inserted into cartons using robotic pick-and-place arms with vacuum grippers. Cartons are sealed with hot melt glue at 165 degrees Celsius and pressed under controlled pressure to ensure full adhesion. Secondary packaging lines aggregate cartons into shipping cases. Cases are erected from flat blanks, filled automatically, and closed with either glue or tape depending on distribution requirements. Completed cases are printed with pallet codes, production timestamps, and destination routing labels. Automated guided vehicles, AGVs, or roller conveyors transfer cases to palletizers. Palletizing robots layer the cases using defined stacking patterns optimized for pallet stability and load efficiency. Each pallet is scanned for completeness, using weight and barcode validation before being stretch wrapped in polyethylene film at 250% pre-stretch. Wrapped pallets are moved to finished goods warehouses with controlled temperature and humidity, typically 18 to 20 C and 50 to 60% RH. Every stage of the process is controlled and logged using a manufacturing execution system, MES. Batch records include ingredient lot numbers, mixing parameters, bake curves, oven temperatures, deposition weights, packaging counts, inspection rejections, and finished product quantities. Quality control technicians collect hourly samples to perform destructive and non-destructive testing on cookies. Tests include diameter measurement with calipers, moisture analysis via moisture, analyzer, texture profile analysis using 3-point bending rigs, and chip count per cookie via manual visual audit. Organoleptic tests include bite resistance, sweetness intensity, and flavor profiling under controlled conditions. Data is stored electronically and checked against specification ranges defined in the product specification documents. Production lines are cleaned on a rotating schedule. Between batches, dry cleaning is performed using brushes and vacuum systems to remove flour dust and crumbs. At daily intervals, equipment is disassembled and sanitized using foaming alkaline cleaners, followed by water rinses and food-safe sanitizers. Chocolate lines undergo specialized cleaning to prevent fat bloom and cross-contamination. Allergen control zones are enforced through physical separation of lines, color-coded tools, and allergen-specific cleaning validations. Swab tests for protein residues are performed on high-contact surfaces after each cleaning cycle. If any allergen residue exceeds the defined limit, cleaning is repeated and verified before production resumes. Downtime events such as depositor jams, film feed interruptions, or oven temperature deviations are tracked via the line control system. Operators record the event time, cause, and corrective actions. Line productivity is measured using overall equipment effectiveness (OEE) metrics, including availability, performance, and quality yield. Preventive maintenance on mixers, ovens, conveyors, depositors, and packaging machines is scheduled based on runtime hours. Critical components such as servo motors, bearings, seal jaws, and roller chains are monitored for vibration and thermal performance. Spare parts inventory is maintained in real time using a computerized maintenance management system, CMMS. Finished product samples are retained from each batch for shelf life testing. These samples are stored under accelerated and ambient conditions and tested at intervals for texture degradation, moisture migration, lipid oxidation, and packaging integrity. Results are used to confirm product expiration dates and to evaluate packaging material performance. All operations conform to global food safety standards such as GFSI benchmarking and are subject to internal audits and third-party certification. Traceability systems allow for immediate upstream and downstream tracking of all product components within minutes of any query. Any deviations from process controls trigger root cause analysis under a corrective and preventive action (CAPA) protocol. McDonald's hamburgers begin with bulk shipments of beef trimmings delivered to centralized processing facilities where the meat is unloaded from refrigerated trucks into chilled receiving bays held between 0 and 4 degrees Celsius. Each lot is inspected visually and mechanically, with camera-based optical sensors and fat analysis probes verifying color, lean content, and moisture levels. Trimmings are sorted by lean to fat ratio to match McDonald's specification for finished patties, typically between 78 and 82% lean. The selected beef portions are conveyed into stainless steel grinding machines fitted with cold jacketed chambers to prevent temperature rise during processing. The grinding heads use fine perforated plates with rotary blades that reduce the muscle tissue into uniform granules of approximately 3-4 µm in diameter. The ground beef is discharged into a horizontal ribbon blender, where any remaining lean to fat variation is equalized through slow speed agitation for 1.5 to 3 minutes. The blended ground beef is then conveyed to an automated portioning and forming line. This system uses volumetric piston feeders that inject exact quantities of meat into stainless steel molds arranged on a rotating turret. Molds are machined to tight tolerances to produce consistent diameter and thickness. Each formed patty is ejected onto a conveyor belt and transferred through a vision-based quality control station that checks for shape deviation, edge defects, and uniformity. Immediately after forming, the patties pass through a metal detector calibrated to identify ferrous and non-ferrous contaminants as small as 1 millimeter in diameter. Acceptable patties are then laid in single layers on perforated stainless steel trays and enter a spiral blast freezer with multi-tiered conveyor belts. Air circulated at 35 degrees Celsius freezes the patties within 6 to 10 minutes, preserving cell structure and preventing microbial growth. Once frozen solid, the patties are robotically stacked into polylined corrugated cartons. Each carton receives a thermal inkjet printout of lot number, facility ID, timestamp, and storage instructions. Cartons are sealed, palletized using 4-way interlocking stacking, wrapped in low-density polyethylene film, and stored in warehouse freezers at 20 degrees Celsius. Pallets are tracked by barcode scanning and integrated into the distribution center's inventory management system. Frozen patties are shipped via insulated trucks equipped with temperature loggers to McDonald's regional distribution hubs. There, they are sorted according to store demand forecasts and loaded onto outbound trucks delivering to individual restaurants. On arrival, each restaurant receives its palletized frozen inventory, which is stored in walk-in freezers held at 18 degrees Celsius or below. During service, frozen patties are manually loaded into refrigerated holding drawers set to 1 to 4 degrees Celsius. From there, they are transferred to a double-sided clamshell grill with heated top and bottom platens. The grill uses preset cooking profiles with digitally regulated temperature zones and timer controls to ensure cooking consistency. The platens press down with calibrated force to ensure uniform contact and searing across the entire surface. Cooking temperatures are typically set between 218 and 232 degrees Celsius. Contact grilling sears both sides simultaneously, allowing internal temperatures to reach a minimum of 69 degrees Celsius within 38 to 45 seconds, depending on patty thickness. Internal thermocouples and surface heat sensors validate cooking cycle completion. Cooked patties are transferred to a heated holding cabinet set to 65 degrees Celsius with a maximum residence time of 15 minutes. Hamburger buns are delivered from third-party commercial bakeries in sealed plastic bags, stored at ambient room temperature. Each bun is pre-sliced horizontally and stored in dry shelving units. At the point of order, buns are transferred into a bun toasting system that uses a pair of vertically aligned platen heaters. The interior face of each bun half is pressed briefly against a 290 Celsius hot surface for 8 to 12 seconds, resulting in light browning and moisture barrier formation. Buns are then transferred to the assembly line, where a standardized sequence of condiments is applied. Condiment stations are calibrated to dispense fixed volumes per activation. Ketchup and mustard dispensers are gravity-fed with pneumatic pumps, delivering approximately 2.2 grams of ketchup and 1.5 grams of mustard per burger. Diced onions are stored in chilled bins and applied using pre-measured scoops to maintain serving consistency. Pickles are stored in brine within covered cold pans and dispensed using tongs or measured forks, with each sandwich receiving 2 pickle slices. If the burger includes cheese, processed cheese slices are stored in a heated drawer at 30 to 35 degrees Celsius to retain pliability and avoid breakage. A single slice is placed directly on the hot patty to allow softening from residual surface heat. Cheese is never reheated directly to avoid oil separation or rubbery texture. The patty is placed on the heel of the bun, aligning it center to edge within a maximum deviation of 5 millimeters. The crown of the bun, bearing condiments and toppings, is pressed onto the patty with light manual pressure. The assembled burger is placed into a food-grade cardboard clamshell labeled with SKU and timestamp. The product is immediately transferred to a chute or pickup station, depending on whether the order is dine-in, takeout, or drive-through. All ingredients and subsystems are governed by an electronic kitchen management system. This system tracks inventory movements, cooking cycles, and holding times in real time. The grill communicates with the central controller via embedded microcontrollers. Alerts are generated when product remains on the grill or in the holding unit beyond preset time limits. Cleaning and maintenance schedules are defined per equipment type. The grill surfaces are cleaned with non-abrasive pads between cycles, with a full disassembly and detergent cleaning conducted during low-volume hours. Bun toasters, condiment dispensers, and heated drawers are sanitized using food-safe cleaners at daily intervals, logged manually in inspection sheets. Cooking oil from other station components, such as fryers, is not used in hamburger production. However, grill grease is collected through internal drainage channels and directed into a sealed grease trap located below the cooking surface. These traps are emptied by third-party disposal services following regulatory standards for food service waste. Employee actions in burger assembly are standardized through training modules and visual process flow guides posted at the station. Assembly steps, ingredient order, and portion control are not subject to personal variation. A deviation beyond defined tolerance, for example, 3 pickles instead of 2, would be logged as an error in the station's quality control record. Ingredient restocking occurs during shift change or low traffic periods. Cheese, onions, buns, condiments, and patties are replenished by staff using designated procedures to ensure oldest inventory is used first. Expiry times are marked on all trays using color-coded labels or dry erase markers based on current health code regulations. The overall process from freezer to assembled burger takes approximately 3 minutes, with cooking accounting for less than half that duration. Each burger conforms to predefined standards for temperature, weight, ingredient distribution, and presentation. Random audits by shift managers and corporate inspectors validate conformity, and deviations are recorded in digital quality logs. At the end of service, all remaining patties in the holding cabinet are discarded if they exceed the 15-minute maximum hold window. Waste is recorded for internal tracking, and excess is analyzed during shift reports to optimize future grill loading decisions. Allergen control protocols are in place for products containing cheese or bun components processed in facilities that handle wheat, soy, or dairy. Equipment used for allergen-containing items is cleaned using verified procedures before cross-contact sensitive menu items are prepared. Burger King hamburgers begin at industrial-scale meat processing facilities, where fresh beef trimmings are delivered in vacuum-sealed containers maintained below 4 degrees Celsius. The trimmings are offloaded into chilled receiving areas equipped with stainless steel conveyors and holding bins. The bins feed directly into grinders fitted with cutting plates calibrated to a precise perforation diameter between 3.2 and 4.8 millimeters. The grinding process is conducted under controlled temperatures to prevent protein denaturation and inhibit microbial growth. The ground beef is transported via enclosed auger systems into horizontal ribbon blenders that homogenize the mixture to a target lean-to-fat ratio of approximately 80-20. Blending continues for 90 to 120 seconds at low RPM to avoid heat buildup. Each batch is sampled for moisture content, fat dispersion, and microbial contamination. No seasonings, fillers, preservatives, or additives are introduced. Quality-approved batches are routed directly to the forming line. The forming process uses hydraulic form and eject systems with rotary dies that compress the meat into circular patties of fixed mass, diameter, and thickness. Optical sensors monitor patty integrity, checking for cracks, underfilled molds, or edge defects. Formed patties are placed onto poly-coated food-grade conveyor belts and immediately pass through a metal detection tunnel calibrated to detect ferrous and non-ferrous contaminants as small as 1.0 millimeter. Patties then enter a spiral freezer where air chilled to 35 degrees Celsius circulates at high velocity to harden the product within 7 to 10 minutes. Rapid freezing limits ice crystal growth and preserves cell structure. Upon exit, frozen patties are automatically stacked in counted layers into polyethylene-lined cartons. Each carton is sealed, labeled with a unique batch code, production timestamp, and storage requirements, then palletized and transferred to cold storage held at 20 degrees Celsius or lower. Frozen patties are shipped in refrigerated trailers equipped with continuous temperature logging devices that provide data on transit conditions. At Burger King distribution centers, incoming pallets are scanned into inventory and stored in walk-in freezers. Orders are fulfilled based on store demand algorithms, with frozen patties delivered to individual restaurants on a rotational inventory system that ensures first in, first out usage. At the restaurant level, frozen patties are stored in low-temperature freezers until transferred to refrigerated drawers for same-day cooking. Each drawer maintains internal temperatures between 1 and 4 degrees Celsius. Restaurant operations follow a grill-to-order or batch preparation method depending on volume. Cooking is done using a proprietary gas-fired broiler system equipped with a continuous stainless steel chain conveyor that transports raw patties through a tunnel with overhead and under-fired direct flame burners. Each patty is manually placed onto the moving broiler belt, which advances at a fixed speed preset according to patty thickness and desired internal temperature. As the patty enters the broiler tunnel, infrared sensors verify burner ignition and temperature stability. The open flame directly contacts the surface of the patty, inducing a Maillard reaction that produces characteristic grill marks and seared flavor. Simultaneously, moisture is driven out of the meat surface, concentrating the flavor and forming a firm exterior crust. The broiler conveyor moves at a calibrated pace, typically between 2.5 to 3.5 minutes per pass, depending on the product type. Internal temperatures of patties are monitored via embedded thermocouples in test units during hourly quality assurance checks. Each patty must achieve an internal temperature of at least 71 degrees Celsius before being passed to the holding area. The broiler is equipped with grease drainage systems that collect rendered fat into heat-resistant trays, which are emptied and cleaned daily. Cooked patties are deposited onto a stainless steel chute that guides them into heated holding trays. These trays are equipped with radiant heat elements that maintain surface temperatures between 60 and 65 degrees Celsius. A digital timer tracks how long each tray has been loaded. Cooked patties are held for a maximum of 10 minutes before being discarded to maintain texture and taste consistency. Each tray is labeled with a batch code and timestamp for traceability. While patties are cooking, buns are processed through a vertical bun toaster equipped with conveyor-style platen heaters. Buns are stored at room temperature in sealed bags until loaded into the toaster's gravity-fed chute. Each bun is sliced horizontally, and the interior face is pressed against a heated platen set to 288-293 degrees Celsius for 9 to 11 seconds, producing a lightly toasted surface that provides moisture resistance and structural stability during sandwich assembly. At the assembly station, buns are transferred to stainless steel prep surfaces. Condiments are applied using calibrated squeeze bottles or piston-driven dispensers. Mayonnaise, ketchup, and mustard volumes are controlled to within 0.2 gram tolerance per sandwich. Pre-chopped lettuce is stored in refrigerated bins held at 1 to 4 degrees Celsius and portioned with measured scoops. Sliced tomatoes are machine cut off-site to uniform thickness and stored in cold bins. Pickles are pre-sliced, stored in brine, and dispensed manually or by volume-controlled tongs. Onion slices are separated into rings and stored dry in chilled compartments. Cheese slices, individually separated by interleaving sheets, are held in humidity-controlled drawers and applied manually to hot patties. Melting begins on contact due to retained surface heat from the broiler. In multi-patty configurations, cheese is placed between layers to bind them together. Burger crowns are pressed gently onto the sandwich to complete assembly. Each finished burger is placed into a pre-folded paper wrap or cardboard clamshell, depending on store packaging configuration. Clamshells are preloaded into gravity-fed dispensers and labeled with SKU identifiers. Assembly staff insert each item into its respective packaging within 10 seconds of completion to reduce heat loss. Packaged burgers are queued on heat-retaining stainless steel chutes until collected by frontline staff or drive-through personnel. All steps of production, from raw patty to finished burger, are logged via point-of-sale integrated kitchen management systems. These systems track timestamps for cook cycles, holding durations, and ingredient usage. Broiler temperatures, toaster settings, and holding bin temperatures are verified hourly against digital readouts and documented in quality assurance logs. Ingredient rotation follows a strict first in, first out schedule. Bins for lettuce, tomato, and onions are marked with timestamps. Condiment cartridges are replaced every 4 hours. Cheese drawers are sanitized every 4 hours or upon visible residue. Packaging materials are stored in dry areas above floor level and inspected daily for contamination or damage. Cleaning procedures for the broiler include nightly shutdown and disassembly of the chain, flame shields, and drip trays. Components are soaked in degreasing solution, brushed with food-safe abrasives, rinsed with potable water, and reassembled before morning operations. Bun toasters are wiped down between shifts and deep cleaned daily. Stainless steel prep surfaces are sanitized using quaternary ammonium-based solutions between each menu changeover. Waste patties beyond holding limits are recorded and disposed of according to local food safety regulations. Waste logs categorized by reason: overcooked, expired holding time, or off-spec grill temperature. Daily waste volumes are analyzed against hourly demand forecasts to optimize future batch sizes and reduce discard rates. Every element of the system is engineered for reproducibility. Conveyor speed, burner placement, heating element calibration, and ingredient flow are all configured to produce identical results across every store. Burger King's operational procedures specify not only the quantity of each topping, but the order of application, spacing, and placement centering to reduce variability. Thermal cameras and real-time temperature logging are used in some test markets to improve process control. Wendy's hamburgers begin with the processing of fresh, never frozen beef. Whole muscle cuts are delivered to regional patty processing facilities in refrigerated containers held between 0 and 4 degrees Celsius. These cuts are trimmed of excess fat and connective tissue by mechanical blade systems equipped with thickness sensors and cutting guides to standardize input material. The trimmed beef is passed through fine grinding plates with perforation diameters ranging from 3.5 to 5.0 millimeters to produce uniform ground meat. The ground beef is loaded into stainless steel mixing tanks where the lean to fat ratio is balanced to approximately 80.20 using real-time fat analysis sensors and automated auger feeding systems. No preservatives, fillers, or additives are introduced. The blend is mixed gently under chilled conditions to prevent protein degradation and to retain water binding capacity. The mixture is tested for microbial content, temperature, and compositional accuracy before advancing. Patties are formed using hydraulic forming machines with square dies, giving Wendy's burgers their distinctive shape. Each mold is calibrated for precise weight and thickness, typically 113 to 170 grams, depending on the product line. Formed patties are transferred to a conveyor where machine vision systems inspect for edge defects, cracks, or inconsistencies in surface texture. Acceptable patties are placed into single-layer, vacuum-sealed packaging and labeled with production time, lot number, and expiration date. Packaged patties are transported to restaurant locations via refrigerated trucks maintained below 4 degrees Celsius. Upon arrival, the patties are stored in walk-in refrigerators with air circulation systems designed to maintain uniform temperatures and humidity. The storage area uses FIFO inventory rotation, tracked by internal labeling systems that log delivery and use dates. Patties are removed from cold storage and transferred to a flat-top grill for cooking. The grill is made of polished steel and heated by independently controlled heating zones, maintained at temperatures between 218 and 246 degrees Celsius. Cooking surfaces are checked for temperature consistency using surface thermometers before each service period. No oil is added to the grill surface, as the beef renders its own fat during cooking. Raw patties are placed directly on the hot surface and pressed with a weighted spatula to ensure even contact and browning. The searing process forms a crust that locks in juices and enhances flavor through Maillard reaction. Internal patty temperature is monitored using digital thermometers to ensure a minimum internal temperature of 71 degrees Celsius is reached. Cooking time ranges from 3 to 4.5 minutes per side, depending on patty thickness and grill load. Patties are flipped once during cooking using flat-edge spatulas to maintain structural integrity. Drippings are channeled into built-in grease traps that are emptied and cleaned daily. Finished patties are transferred directly to a heated holding tray set to maintain product between 60 and 65 degrees Celsius. Holding time is limited to 5 minutes to ensure texture and flavor integrity. Burger buns are delivered from certified commercial bakeries, stored in ambient conditions in dry storage areas, and used within labeled shelf life. Buns are sliced in-store using serrated rotary cutters attached to prep tables. Each half is toasted on a separate bun toaster fitted with heated platens that reach 285 to 295 degrees Celsius. Toasting duration is controlled to within 0.5 seconds per bun half to ensure uniform color and surface dryness. Toasted buns are transferred to the sandwich assembly station, where standard build sequences are followed. The sandwich station includes dedicated zones for condiments, vegetables, cheese, and protein. Mayonnaise and ketchup are dispensed using piston-based systems with adjustable volume control set to deliver consistent amounts per sandwich. Mustard and other optional sauces are applied manually in measured dollops using portion-controlled utensils. Fresh lettuce is shipped pre-cut and triple washed, stored in refrigerated prep tables between 1 and 4 degrees Celsius. Tomatoes are sliced daily using mechanical slicers to a thickness of 5 millimeters and stored in high humidity containers. Onions are peeled and sliced into rings and portioned by visual estimation or scale weight. Pickles are brined and pre-sliced, dispensed using tongs from refrigerated compartments. Cheese is individually sliced and stored in covered trays within the sandwich station's cold section. A single slice is placed directly onto the hot patty immediately after cooking. The heat from the patty softens the cheese, but does not fully melt it, preserving slice definition. Bacon, if added, is cooked separately on a flat-top griddle and held in warming drawers lined with absorbent paper and heated via low-voltage infrared elements. Assembly order follows strict guidelines. The bottom bun receives sauces and condiments, followed by lettuce, tomato, and onion. The patty is placed on top of vegetables to reduce heat transfer to the bun. Cheese, bacon, and pickles are layered above or below the patty based on product specifications. The crown bun is pressed on top to complete the build. Assembled burgers are wrapped in branded foil wrappers or placed in paperboard containers depending on order type. Wrappers are designed with heat-retaining layers and moisture vents. Burgers are staged in a holding chute or placed directly into order bags. All packaging materials are stored in dry stock rooms and replenished daily. Package weight and sandwich construction are audited periodically for consistency. Restaurant kitchens use an operations management system that logs grill usage, cooking cycles, and holding times. Thermocouple sensors embedded in the grill surface provide live temperature feedback. Digital timers alert staff when patties must be removed or discarded. Each station is monitored for compliance with production procedures via internal checks and periodic inspections. Cleaning schedules are programmed to occur at shift changes and closing. Flat-top grills are scraped after each use and cleaned with food-safe degreaser at the end of each day. Grease traps are emptied, wiped, and sanitized using quaternary ammonium-based disinfectants. Prep surfaces are wiped with single-use sanitizer wipes and tested with ATP swabs for surface cleanliness verification. Unused raw patties at the end of the day are discarded if past time limits. Opened, condiments are sealed and stored in designated cold storage with labeled expiration dates. Open vegetable containers are covered with plastic film and labeled with the date and time of preparation. All leftovers are monitored for spoilage indicators and disposed of if they exceed quality thresholds. Each restaurant uses a real-time inventory and supply tracking system linked to a central database. Usage rates for beef, buns, vegetables, cheese, and condiments are analyzed against sales data. Discrepancies trigger alerts to management and may result in retraining or procedural audits. Ingredient reorders are generated automatically based on projected demand using historical sales averages. Allergen control measures are implemented in burger production through equipment segregation and cleaning protocols. Separate spatulas and prep zones are designated for allergen-free products. Staff receive allergen training and use visual cue systems to avoid cross-contact. Labels indicate allergen presence per local regulatory requirements. Throughout the process, every input is controlled and verified to produce uniform hamburgers across locations. Cooking parameters, ingredient measurements, and build sequences are optimized for speed, consistency, and quality. Final products are subject to visual inspection, temperature checks, and build verification by designated shift managers. Any deviations are logged and addressed through corrective procedures. In a modern Oreo manufacturing facility, key dry ingredients are delivered in bulk, often by rail cars or food-grade trucks, and are pneumatically conveyed into large storage silos made of stainless steel or epoxy-lined carbon steel. These silos are sealed from air and moisture and are connected to the factory's central control system. The main dry ingredients include unbleached, enriched wheat flour, processed cocoa powder, granulated sugar, and minor dry components like baking soda and salt. Each of these materials is handled in its own silo or hopper, and automated augers or vibratory feeders dispense precise quantities into batch weighing hoppers. These hoppers sit on load cells, sensitive scales that can measure down to a fraction of a gram. This is essential because the correct ratio of flour to cocoa to sugar directly affects not only the flavor, but also how the dough behaves under pressure during molding. If the cocoa content is even slightly too high, for instance, the dough may become too brittle and crack during forming. If it's too low, the wafers may bake up too soft, losing the crisp snap that defines an Oreo. Once the dry materials are batched, they are conveyed into a pre-mixing chamber. At this stage, powdered ingredients are briefly tumbled together to ensure initial homogeneity before liquids are added. Then it's time for the liquid components to enter the system. These include vegetable shortening, often a blend of palm and canola oil, along with a sugar syrup or glucose solution, invert sugar, lecithin, and vanillin or other flavoring agents. The fats and liquids are stored in temperature-controlled tanks and are metered into the mixer through heated pipes. The temperature of the fats is critical. Too cold, and they won't disperse evenly. Too hot, and they could melt too aggressively, breaking down the emulsion and affecting dough integrity. All of these components are combined in large jacketed horizontal mixers or double sigma arm batch mixers. These mixers are chosen for their ability to handle heavy, cohesive doughs while still ensuring thorough dispersion. Inside the mixer, paddles or blades knead the dough continuously, folding and stretching it to develop a uniform texture. The mixer operates under a specific time and speed profile, starting slow to incorporate the dry and wet components, then increasing speed to blend, then finishing with a gentle knead to avoid overworking the dough. The goal here is a dough that's soft but not sticky, cohesive but not tough. Sensors inside the mixing chamber monitor temperature and torque, two key indicators of dough readiness. If the dough becomes too warm from friction, it can become greasy and difficult to form clean edges in the molding machines. If it's undermixed, the ingredients won't be uniformly distributed, and inconsistencies in cookie size, color, and bake profile will result later on. Once the dough reaches its target specifications, it's discharged from the mixer through a hydraulically controlled trapdoor at the base of the mixing tank. The dough falls into a dough transport system, typically a set of conveyors or troughs lined with non-stick materials like Teflon or food-grade UHMW polyethylene. At this stage, the dough may still be slightly warm, around 30 degrees Celsius to 35 degrees Celsius, and has a dense, matte appearance with a strong cocoa aroma. Before moving to the forming machines, the dough must undergo a resting period in certain operations. This allows the flour to fully hydrate and any residual gases or trapped air to escape. In high-speed production environments, however, this rest period may be minimized or skipped altogether if the formulation is optimized for immediate processing. This completes the initial phase: ingredient intake, formulation, mixing, and dough discharge. Each step up to this point is carefully controlled by recipe management software that ensures no human error can affect batch consistency. Recipe locks, scanner-based operator identification, and redundant scale verification ensure each batch of Oreo wafer dough is made precisely to the specifications required to perform flawlessly in the next stage of the journey: shaping and embossing. Now that the chocolate wafer dough has been prepared with absolute precision, measured, mixed, and conditioned, it moves into one of the most visually iconic and mechanically fascinating phases in the Oreo production line: forming and molding. This step takes the dense, cocoa-rich dough and transforms it into thousands of uniformly sized, detailed cookie wafers, each embossed with the distinctive Oreo pattern. This is not simply cutting shapes out of dough, it's a highly engineered, high-speed process where consistency in shape, thickness, and surface detail must be maintained across millions of units every day. The freshly prepared dough is conveyed to a hopper positioned above a sheeter. This sheeter is a wide, stainless steel roller assembly that flattens the dough into a uniform sheet of specific thickness. The dough moves between a set of rollers, typically 2 or more steel cylinders calibrated to exact tolerances that compress it to the target height. For Oreo wafers, the final sheet is quite thin, often around 3 to 4 millimeters, with a consistent density and moisture distribution. Getting this thickness right is critical. If the sheet is too thick, the cookie may not bake evenly or could become too brittle. Too thin, and the cookies may crack, burn, or crumble during sandwiching. Sensors measure the thickness of the sheet continuously using laser or ultrasonic gauges. If deviations are detected, servo-driven actuators automatically adjust roller spacing to maintain precision. The sheeter also includes edge trimmers, small, motorized blades that cut off uneven or frayed edges of the dough sheet to keep the line uniform. The trimmed edges are collected by a scrap recovery system and reintroduced into the mixing system, minimizing waste without compromising freshness or quality. Once the dough sheet is perfected, it enters the rotary molder. This machine is central to the Oreo brand's identity, as it forms the shape, size, and embossed design of each cookie wafer. The rotary molder consists of two primary components, a rotating die roller and a pressure roller. The die roller is a cylindrical drum engraved with multiple cavities, each one precisely carved with the Oreo design. These cavities aren't just cosmetic. Their depth and contour dictate the final relief of the cookie surface. As the dough sheet passes between the die roller and pressure roller, each cavity punches into the dough, compressing it into shape and imprinting the Oreo design. The pressure roller, covered in food-safe rubber or polymer, pushes the dough up into the die cavities, ensuring a clean, complete mold. As the die drum continues rotating, the shaped wafers are extracted by a combination of mechanical pushes and vacuum assist systems, which gently remove the cookies from the cavities without smudging the design. These freshly molded cookie wafers are then transferred onto a wide mesh conveyor belt in a continuous, uninterrupted line. Each wafer is spaced evenly to allow for proper airflow in the next phase, baking. Meanwhile, the excess dough surrounding the cutouts, known as webbing, is carefully separated and sent back through the scrap system. This recovery loop is highly efficient, capturing nearly 100% of the unused dough and returning it to the mixer via chilled transport belts. To ensure product consistency, reworked dough is blended at a fixed percentage into fresh dough, preventing any changes in texture, flavor, or moisture that might result from over-processing. As the line of uniform, molded Oreo wafers advances, they approach the baking tunnel, one of the most thermodynamically sophisticated parts of the facility. The tunnel oven is a massive structure, often exceeding 30 meters in length, segmented into multiple temperature-controlled zones. Each zone is precisely tuned to manage the gradual dehydration and expansion of the cookie, ensuring even baking from edge to center. The ovens use convection, conduction, and in some cases, radiant heat, depending on the equipment manufacturer and regional factory specifications. The cookie wafers bake as they travel slowly through the tunnel, typically for a duration of 4 to 6 minutes. Conveyor speed, airflow rate, and internal oven temperatures are continuously adjusted via programmable logic controllers that interface with sensors monitoring internal humidity, surface temperature, and even color of the baking cookies using infrared imaging systems. The target bake is one where the cookie becomes crisp and fully set while retaining a slight moisture gradient at its core, enough to ensure it sandwiches cleanly without shattering, and holds up in milk without becoming soggy too quickly. Another crucial parameter monitored at this stage is cookie spread and diameter. Because the molded wafers expand slightly as they bake, their final size must fall within a fraction of a millimeter to ensure they'll match perfectly with their paired half during sandwiching. Edge blowout, where cookies develop uneven bulges or bubbles, is prevented by careful control of initial dough temperature, mold compression depth, and oven humidity during the first baking phase. As the cookies exit the oven, they are immediately passed through a staged cooling system. This phase is designed to gently bring the cookies from their internal post-bake temperature of roughly 160 degrees Celsius down to ambient room temperature. Cooling too quickly can cause the wafers to crack, warp, or experience checking, tiny surface fractures that affect aesthetics and structural integrity. To avoid this, The conveyor slowly moves the wafers through a series of cooling zones with progressively decreasing airflow temperatures. High-volume fans push filtered, dehumidified air over the wafers in a cross-flow pattern that cools them evenly on all sides. By the time the wafers reach the end of the cooling tunnel, they are firm, crisp, and at a stable moisture level, typically around 1.5% to 2%. This ensures maximum shelf life, a satisfying crunch, and ideal compatibility with the creme filling in the next phase of production. They are now ready for alignment and pairing. Wafers are automatically aligned into dual streams using diverters and channeling guides. Conveyor belts, equipped with vision systems, scan for defects such as missing embossing, chips, discoloration, or breakage. These systems use high-speed cameras and AI-assisted pattern recognition to detect any imperfections in milliseconds. Rejected cookies are diverted to a waste collection hopper, and approved wafers continue forward to the sandwiching stage. With the Oreo chocolate wafer cookies fully formed, baked, and cooled, the production line now transitions into one of the most iconic and mechanically synchronized parts of the process: sandwiching. This stage involves the precise alignment of two delicate wafer halves around a carefully deposited swirl of creme filling, forming the complete Oreo cookie as we know it. What may seem like a simple task, placing filling between two cookies, is in fact a highly controlled and technically advanced process that prioritizes speed, accuracy, hygiene, and product consistency. The cooled wafers arrive at the sandwiching station via dual-lane conveyors that separate and feed cookies into two different orientations: bottom wafers and top wafers. The bottom wafers are destined to receive the cream filling, while the top wafers are held back momentarily, synchronized to arrive just as the filling has been deposited. Vision-guided pick-and-place arms or mechanical guides ensure that each cookie is properly positioned and oriented with the embossed design facing upward, especially important for branded recognition in the final presentation. The placement needs to be exact. Even a slight misalignment could result in uneven sandwiching or a crooked creme center, which would be rejected downstream. At the heart of the sandwiching line is the creme depositor. This component is engineered to dispense a precise amount of creme onto the center of each bottom wafer. The creme filling itself has been prepared earlier in the process and is stored in stainless steel holding tanks near the sandwiching line. The base creme is a blend of vegetable shortening, powdered sugar, and natural or artificial flavorings, aerated to achieve a smooth and creamy texture. It is kept at a controlled temperature, typically between 25 degrees Celsius and 30 degrees Celsius, to maintain flow consistency without being too runny or too firm. The creme is pumped into the depositor through a jacketed delivery line, which maintains temperature and prevents any hardening or separation. Inside the depositor, a rotary valve system or piston-driven nozzles release measured quantities of filling in circular swirls directly onto each passing wafer. The target deposition amount is extremely precise, usually around 3 grams per cookie for the original Oreo. For double stuff, the system is calibrated to deliver twice that volume, and the depositor nozzle height is adjusted accordingly to accommodate the larger swirl. The deposition speed is synchronized with the conveyor, meaning each swirl is deposited while the bottom wafer is in motion. To maintain consistent swirl shapes, the nozzle spins at a high RPM as it dispenses the cream. Sensors and imaging software track swirl size, height, and position. If the deposit strays from the central zone or falls outside weight tolerances, that cookie is automatically flagged and diverted. These sensors run continuously, sampling thousands of cookies per minute with extremely tight thresholds for variance. Once the creme is in place, the top wafer is gently placed onto the swirl. This is done by an overhead transfer arm or drop chute designed to lower each top cookie into place with just enough pressure to make contact without squashing the filling. The timing here is critical. Placing the top wafer too early could create smearing or incomplete adhesion, while placing it too late could allow the creme to set and result in a loosely held sandwich. Once the two halves make contact, a calibrated compression roller or paddle gently presses them together to create a uniform sandwich with a visible, even creme edge. The newly assembled Oreo cookies are then conveyed forward to undergo another round of quality inspection. At this stage, high-speed vision systems again scan for defects. These include cracked or broken wafers, misaligned sandwiches, off-center cream, or excess filling that has oozed out past the edges. Cookies that fail to meet standards are ejected via pneumatic pushers or retractable gates, landing in separate bins for non-conforming product. These rejected cookies are either discarded or recycled depending on factory policies and whether they passed earlier food safety checks. The good cookies move on to the next major phase, cooling and setting. Even though the creme filling is solid at room temperature, the act of depositing and sandwiching generates residual warmth, and the filling remains somewhat malleable for several minutes. To stabilize the sandwich structure and ensure long-term integrity during packaging and shipping, the cookies are passed through a controlled cooling tunnel. This tunnel gradually brings the product's temperature down to a stable point, typically just below ambient, which firms up the cream and locks in the sandwich's structural cohesion. As cookies exit the cooling tunnel, they are directed toward the packaging line. Here, the cookies are grouped and arranged into stacks or rows depending on the intended package format, whether it's a classic tray-style retail pack, a resealable pouch, a single-serving sleeve, or a multi-pack unit. For traditional packs, the cookies are guided into channels that group them into stacks, typically of 3 or more, which are then lowered into thermoformed plastic trays by robotic pick-and-place units. These trays help protect the cookies from damage and keep them organized for end-user convenience. Parallel to this, packaging film, pre-printed with branding, nutritional labels, and product information, is unwound from large rolls and fed into a form-fill seal machine. As the cookie-filled trays pass through the machine, the film is wrapped around the product, heat-sealed on all sides, and trimmed to size. Oxygen scavengers or desiccants may be inserted for freshness in some markets, depending on climate and shelf life requirements. For resealable packs, a Ziploc or peel-back adhesive strip is applied as part of the film sealing process, ensuring that consumers can open and close the package without reducing freshness. Each package unit is printed with a lot number, manufacturing date, facility code, and expiration date using high-speed thermal inkjet or laser printers. These codes enable full traceability and are cross-referenced with the production batch data stored in the factory's ERP system. From mixing and molding to creme filling and sealing, every step of the process can be traced back to specific machines, operators, shift schedules, and ingredient batches, an essential feature for food safety compliance and recall readiness. Once sealed, packages are conveyed to automated case packers. Here, robotic arms load the wrapped units into corrugated cardboard cartons, which are then glued or taped shut. These cartons are palletized according to preset patterns that optimize load stability and cube efficiency for shipping. Pallets are wrapped with stretch film, labeled with shipping barcodes and inventory data, and routed to the warehouse staging area. At this point, the Oreo cookies have completed their physical transformation from separate cocoa wafers and creme filling into a polished, fully packaged, ready-to-ship product. But before they leave the factory, they undergo a final quality audit. Samples from each batch are pulled from the finished goods line and tested by in-house sensory panels and laboratory staff. Taste, texture, aroma, appearance, and moisture content are evaluated to ensure that the product not only looks perfect, but delivers the consistent flavor and mouthfeel that Oreo is known for. Moisture levels are especially critical. Too high, and the cookie can lose its crispness during storage. Too low, and it can become brittle or stale. Texture analyzers apply mechanical pressure to the cookies to evaluate crunch resistance and breaking force, while gas chromatography is used to verify flavor compound profiles. Packaging integrity tests include drop tests, seal strength verification, and temperature cycling simulations that mimic transport and storage conditions across various markets. Once these final inspections are passed, the cookies are released for distribution. Pallets are loaded into climate-controlled trucks or containers, routed through regional distribution centers, and ultimately arrive at retail outlets, vending networks, or direct-to-consumer channels. With the Oreo cookie now fully assembled, inspected, packaged, and palletized, the final phase of the in-factory process is dedicated to the logistics, storage, inventory control, and outbound quality assurance systems that prepare the product for global distribution. While it may seem like the technical complexity is behind us, this stage involves its own set of sophisticated workflows designed to ensure that every package remains pristine, traceable, and shelf-stable for months after production, regardless of whether it ends up in a small, rural convenience store or a high-volume urban supermarket. The finished pallets of Oreos are moved from the end-of-line palletizing systems into a dedicated finished goods warehouse. This space is part of the factory complex, but isolated from production to prevent cross-contamination and maintain temperature and humidity stability. Oreo cookies, especially those with creme fillings, are highly sensitive to environmental changes. Excessive heat can soften the filling or compromise the packaging seal, while high humidity can cause moisture migration into the wafer, leading to loss of crispness. To combat these risks, the warehouse is maintained at a tightly regulated temperature, typically between 18 degrees Celsius and 22 degrees Celsius, with relative humidity kept under 50%. The facility is segmented into climate zones for different packaging formats, with certain areas reserved for international shipments that may require added humidity resistance or longer storage durations. Air handlers, industrial-grade dehumidifiers, and air filtration systems constantly regulate and cycle the air to maintain these parameters. Even the lighting systems are designed to minimize UV exposure, which could, over time, degrade packaging ink or food contact films. Once inside the warehouse, each pallet is scanned and logged into a warehouse management system. This system is fully integrated with the factory's enterprise resource planning software and allows operators to track not only where each pallet is stored, but exactly what production line, time, and ingredient lot was used to produce its contents. Each pallet label includes a unique serial number, barcode, and QR code that links to this full production history. This traceability is essential not just for internal logistics, but also for compliance with food safety regulations around the world, which require manufacturers to be able to track every product from raw ingredient to final point of sale. The WMS automatically arranges pallets by product type, batch date, and destination. Those scheduled for export may be routed to a separate staging zone where they will be checked for compliance with international packaging laws. Different markets may require translated labels, adjusted nutritional formats, or modified lot codes. Some export destinations also require additional tests, such as microbial swabs or accelerated shelf life sampling, to meet foreign government regulations. These are performed in an adjacent quality control annex, and only upon clearance are these pallets released to outbound logistics. Before any Oreo shipment leaves the facility, it undergoes a final visual inspection for physical damage to packaging, tamper seals, and box integrity. Any visible damage may indicate mishandling during internal transit or weak spots in pallet stability. Operators are trained to look for warped trays, compromised seals, or even small tears in the flow wrap film that could affect product freshness. Should any defect be discovered, that pallet is held for secondary inspection, and depending on severity, it may be repackaged or scrapped entirely. At this point, logistics coordinators use automated routing systems to schedule outbound shipments. These systems factor in geographic location, delivery deadlines, climate conditions, and truck availability. For example, shipments bound for warmer climates during the summer may be prioritized for insulated or refrigerated trucks to prevent the creme from softening. Long-haul shipments may be routed through distribution centers that offer cross-docking or climate-controlled storage to preserve product quality along the supply chain. The loading dock itself is operated with precision. Trucks arriving at the facility must be cleaned, inspected, and approved before any Oreo products are loaded. This includes visual inspection for pests, residue from prior shipments, and confirmation that the trailer temperature is within specification. Only after a truck passes these inspections does the facility open the dock door and begin the loading sequence. Robotic forklifts or human operators load the pallets according to pre-planned diagrams that ensure weight is evenly distributed and product is easily accessible at the destination. Each shipment is logged with time, driver ID, carrier information, route ID, and estimated delivery window. Once loaded, trucks are sealed with tamper-evident locks and dispatched with digital shipping documents, including delivery confirmations and scanned QR codes for receiving teams. The WMS updates the ERP system in real time, closing the inventory loop and marking the batch as shipped. This inventory and logistics traceability is crucial for meeting compliance with global food safety standards like the Global Food Safety Initiative, hazard analysis, and critical control points, and ISO 22000. Even after the Oreo product leaves the plant, the factory remains connected to its life cycle through digital feedback systems. Retailers and distributors have access to portal-based interfaces where they can report damages, delayed deliveries, or unexpected inventory issues. Returned products are scanned upon arrival at reverse logistics zones where factory staff investigate issues, analyze production records, and determine root causes. In cases where errors are found, such as premature staleness, flavor imbalance, or packaging failure, continuous improvement protocols are triggered to address the upstream causes. While these systems function to protect the product, they also feed into a broader factory goal: performance analytics and continuous optimization. The data from every shipment, temperature logs, shipping duration, breakage rates, seal integrity, and even consumer complaints is compiled into dashboards reviewed weekly by production leads, QA managers, and logistics coordinators. These dashboards enable the factory team to track KPIs like OTIF, defect per million rates, inventory turnover, spoilage reduction, and carbon footprint per pallet. Some Oreo plants are moving even further towards sustainability at this stage of production. Cardboard shipping boxes are made with recycled content and are themselves fully recyclable. Pallet wrap films are being downgauged or replaced with biodegradable alternatives. Facilities are experimenting with hybrid electric fleet partnerships or rail transport instead of trucks to reduce emissions. In select markets, even the plastic trays inside Oreo packs have been redesigned for recyclability, and clear labels now inform consumers on proper disposal.